All right, let's unpack this. Today, we're going deep on storage engines.
The real workhorses behind any database management system, right?
Exactly. That core component that dictates how your data is stored, retrieved, and managed. You might be thinking, isn't the DBMS itself responsible for all that?
It's a common misconception, yeah. The DBMS provides the interface and tools we use to interact with the data, but the heavy lifting, it happens at the storage engine level.
So help me understand this. How would you explain that relationship?
Think of it like this. The DBMS is like, say, a sophisticated app on your phone. Underneath, it relies on the operating system to handle those fundamental tasks.
Okay, like file storage and memory allocation.
Exactly.
So the storage engine is like the Android or iOS for our data.
Yeah, you could say that.
Interesting analogy. So if the DBMS is just an app, what makes the choice of storage engine so critical?
Well, performance, how it directly impacts the user experience. Imagine you're building an app for online shopping here in India.
Millions of users.
Exactly. Browsing products, adding to carts, making purchases. A poorly chosen storage engine. It could lead to, like, sluggish response times, frustrated customers.
Yeah, no one wants to wait ages for a page to load.
Yeah.
Especially when they're trying to buy something.
Right.
So how do different storage engines actually impact performance?
Well, one of the fundamental distinctions is between in-memory and disk-based DBMS.
Okay, as the name suggests, in-memory systems store most of their data in RAM.
Exactly. For blazing fast access, this is ideal for applications where speed is paramount.
Like what?
Like a high-frequency trading platform where milliseconds matter.
But storing everything in RAM, that's got to come with some challenges, right?
Well, yeah.
RAM is volatile. What happens if the power goes out?
That's a valid concern.
Yeah.
To ensure data durability, in-memory DBMSs employ a mechanism called checkpointing.
Okay.
They periodically write the database's state to disk, creating that safety net in case of a system crash.
So it's like hitting save in a video game. You don't lose your progress.
Yeah, exactly like that.
Okay, that's reassuring. But what about disk-based systems? They're the more common type, right?
Absolutely. The workhorses of the database world, they store data primarily on disk.
Okay.
Using memory, mainly for caching frequently accessed data and temporary storage.
So both types utilize disk.
Mm-hmm.
But it seems like in-memory is all about pushing the limits of speed. But I bet keeping an entire database in RAM gets expensive quickly.
You're spot on. RAM is a much more costly resource than disk storage. That's why in-memory DBMSs are typically reserved for applications where performance is absolutely critical.
Yeah.
Real-time analytics, high-volume transaction processing.
So if you're building a system to analyze stock market data in Mumbai, in-memory might be the way to go.
Yeah.
But for small business, like managing inventory, disk-based is probably more practical.
Right.
Now, I'm curious about how data is actually organized within these systems. We often hear about row-oriented and column-oriented databases. What's the difference?
It all boils down to how data is physically laid out on disk. In row-oriented systems, data is stored in rows. All the information for a single record is grouped together.
Okay, like a spreadsheet. Each row represents a customer. The columns contain their details.
Exactly. Name, address, purchase history, and so on.
Okay, that makes sense. So if I'm looking up all the details for a specific customer, row-oriented would be efficient. Well, what if I want to analyze buying trends across all customers?
Yeah.
Wouldn't fetching data column by column be faster?
You're absolutely right. And that's where column-oriented systems shine.
Okay.
Instead of storing data row by row, they store data column by column.
Okay.
This is incredibly efficient for analytical queries where you need to retrieve specific fields across a large number of records.
Right.
Imagine analyzing stock market data. All the historical prices for a particular stock are stored together.
So it's about optimizing for the types of queries you'll be running most frequently.
Exactly.
If you're primarily retrieving entire records, row-oriented is a good choice. But if you're doing a lot of analysis or reporting based on specific fields, column-oriented might be the way to go.
Exactly. The choice of storage engine and data layout is all about understanding the needs of your application and making the trade-offs that best suit those needs.
Now, I'm curious about how this data is actually stored and managed at the file level. What's happening under the hood?
So underneath the interface, we have two main types of files, data files and index files.
Okay.
Data files, as you might guess, are where the actual data resides. One common type of data file is called a heap file. Think of it like a big container where records are added in no particular order, like tossing clothes into a laundry basket.
So it's efficient for adding data quickly, but finding a specific item might require digging through the entire pile.
Right.
That's where index files come in.
You got it. Index files are like a lookup table. They help you quickly locate specific records within the data file. Imagine an index at the back of a book. Allows you to quickly jump to the page containing a particular topic. You have primary indexes built on the primary key of the data file, ensuring uniqueness. And secondary indexes built on other fields, allowing for flexible data access.
So if the data file is a messy laundry basket, the index file is like a neatly labeled set of shelves. Makes it easy to find what you need. But how do these indexes actually work? I've heard of data structures called B-trees being used here. Is that right?
You're right on the mark. B-trees are a foundational data structure often used to implement indexes in storage engines.
Okay.
They're incredibly efficient for searching, inserting, and deleting data, especially when dealing with large data sets stored on disk. What makes B-trees so interesting is that they're built from the bottom up, unlike many other tree structures.
From the bottom up?
Yeah.
That seems counterintuitive. Why build a tree that way?
Yeah. It's all about minimizing costly reorganizations. B-trees are designed to work optimally with disk-based storage, which is inherently slower than RAM.
Right.
By building from the bottom up, they reserve space for future insertions and updates, reducing the need to move large chunks of data around on disk.
So it's like designing a closet with extra space built in, so you don't have to rearrange everything every time you buy a new shirt.
Exactly.
Clever. But what happens when a B-tree node gets full? Does it need to be split, leading to those reorganizations we're trying to avoid?
That's a great question. And it leads us to another ingenious aspect of B-trees, overflow pages. Imagine you have a fixed size box and you need to store items of varying sizes. Overflow pages allow the storage engine to handle this gracefully.
Okay.
Instead of forcing a larger box, additional pages are linked to the original box to accommodate larger pieces of data.
So it's like having those under-the-bed storage containers for when your closet gets full. You don't have to rebuild the entire closet just to fit a few more items?
Precisely. And this is just one example of how clever engineering decisions in B-trees lead to significant performance gains in database systems. We've talked about how B-trees ensure efficient data access, but there's another critical aspect of storage engines, ensuring data integrity.
Data integrity, right? We touched on checksumming earlier. It's like a quick scan for obvious errors. But are there other mechanisms at play to guarantee the reliability and correctness of data?
Absolutely. Checksumming is a good first line of defense, but storage engines employ a whole arsenal of techniques to safeguard data integrity. One important concept is the idea of a transaction. Think about transferring money between bank accounts. You wouldn't want the transaction to partially complete. It's all or nothing.
That makes sense. You either debit one account and credit the other, or you don't do it at all. No room for half-finished transactions. But how do storage engines guarantee this all-or-nothing behavior?
They use a mechanism called write-ahead logging. Think of it like a meticulous journal that records every step of a transaction before it's actually applied to the database. If something goes wrong, the storage engine can use this log to roll back the changes, ensuring the database remains in a consistent state.
So it's like having a safety net, allow you to undo any mistakes.
Right.
That's crucial for maintaining data integrity. But what about situations where multiple users are trying to access and modify the same data simultaneously?
Yeah.
How do storage engines prevent conflicts and ensure consistency?
That's where concurrency control comes into play. Imagine a scenario where two people try to withdraw money from the same account at the same time. Without proper concurrency control, you could end up with an incorrect balance.
So it's like having a traffic cop at a busy intersection, directing the flow of data and preventing collisions.
Exactly.
How do storage engines achieve this?
One common approach is locking. Before a user can modify a piece of data, they need to acquire a lock on it, preventing others from making changes at the same time. This ensures that changes are made in a controlled and orderly manner, preserving data integrity and consistency.
It's like putting a do not disturb sign on your data while you're working on it. Okay, I'm starting to see how all these mechanisms, checksumming, transactions, concurrency control, work together to create a reliable and robust storage engine.
Exactly. And there's even more to explore. We've discussed heap files, but there are other types of data files with their own unique characteristics and performance trade-offs.
Like?
For instance, we have index-organized tables and hash-organized tables.
Okay, those sound a bit more structured than the heap file analogy we discussed earlier. What are the key differences?
Index-organized tables, as the name suggests, store data in the order of the index. This can be very efficient for certain types of queries. Imagine a phone book where the entries are already sorted alphabetically. No need to flip through pages randomly.
Makes sense. And what about hash-organized tables? How do they work?
They use a hash function to determine where data should be stored. This can be very efficient for looking up individual records, like having a library where each book has a unique call number that tells you its exact location on the shelves.
So it's like having a system where you know exactly which drawer to find a specific item based on a predefined logic. I'm starting to grasp the variety of data organization techniques used in storage engines, but I imagine choosing the right structure is just the first step. There's also the question of how those structures are actually implemented on disk, right?
Absolutely, and this is where things can get even more intricate. We have to consider factors like page size, layout, and how data is serialized. Think of serialization as translating your data into a language that the disk can understand.
Like encoding and decoding messages. I remember our conversation about endianness and how byte order can impact data interpretation. Is that something storage engine developers need to consider as well?
Absolutely. Endianness or byte order is crucial for data portability and interoperability. A storage engine in Delhi needs to be able to read data written by a storage engine in Chennai, even if they use different hardware with different byte ordering schemes.
So storage engines need to be multilingual, ensuring data can be understood no matter where it travels.
Precisely. And on top of byte order, there are different data types to consider: integers, floating point numbers, strings, and so on. Each requires careful handling during serialization.
I can only imagine the complexity involved. And to make things even more challenging, we have to consider how to manage free space, how to handle updates and deletions efficiently, and how to optimize for performance given the physical limitations of disk storage. It's like a carefully choreographed dance, balancing data organization, storage efficiency, and retrieval speed.
It's an intricate dance indeed. And to add another layer of complexity, we have to ensure that these intricate mechanisms are robust enough to handle unexpected events, like power outages, hardware failures, or even software bugs. In the real world, things don't always go according to plan.
That's a great point. You can't just assume everything will always work perfectly. How do storage engines handle these real-world challenges?
Well, one crucial aspect is recovery. If a system crashes, the storage engine needs to be able to restore the database to a consistent state. It's like having a backup plan, a way to pick up the pieces and rebuild after a disaster.
So it's like having a time machine for your data.
In a way, yes. To achieve this, storage engines use techniques like logging and checkpointing. Logging, as we discussed earlier, provides a detailed record of changes. Checkpointing periodically saves a snapshot of the database's state to disk.
Wow.
So even if the system crashes, you can use these records to reconstruct the database and get back on track.
That's incredible. It's like having a safety net that ensures you can always rewind and recover from any mishaps.
Yeah.
But what about scaling beyond a single machine? What happens when you need to handle massive amounts of data or distribute your database across multiple servers? We've talked about single machine storage engines so far. What about distributed databases? How do they handle data storage and retrieval across multiple machines?
That's a fantastic question, and it leads us into the fascinating world of distributed storage systems.
Hold on. Let's save that adventure for next time. We've covered so much ground already, and I'm sure our listeners could use a moment to digest all this information. We'll be back soon to explore the world of distributed databases and the clever ways storage engines tackle the complexities of managing data across multiple machines. Stay tuned.
Welcome back. Before we take that leap into distributed databases, I think it's worth highlighting a few more intricate details of single machine storage engines. We were just discussing how they handle unexpected events.
Right, ensuring data integrity even when things go wrong. It's fascinating how storage engines act like guardians of our data, protecting it from corruption, inconsistencies. What other safeguards are in place?
One crucial mechanism is replication. It's like having multiple backup copies of your data, but with a twist.
Okay, we touched on replication briefly earlier, creating those redundant copies. But how do you make sure they all stay in sync, especially if there are like hiccups in the network or some servers are temporarily unavailable?
That's where things get really interesting. Storage engines rely on sophisticated techniques. like consensus algorithms to ensure consistency across these replicas.
Consensus algorithms. That sounds intense. Break it down for me. What exactly are we talking about here?
Imagine a group of people trying to make a decision, but some are out of contact or have conflicting opinions. A consensus algorithm helps them reach a unified outcome despite these challenges. In the context of storage engines, it's a way for all the nodes in a distributed system to agree on a single consistent view of the data.
So even if some servers are down or the network is acting up, the consensus algorithm ensures that all the remaining servers eventually converge on the same state, maintaining data consistency across the replicas.
Exactly. There are various consensus algorithms, each with its own strengths and weaknesses, but they all aim to achieve agreement among the nodes, even in the face of adversity.
That's pretty impressive. It's like having a built-in mediator that ensures everyone stays on the same page no matter the chaos. But I'm curious about how this actually plays out in a distributed database. How do storage engines use these consensus algorithms in practice?
One common approach is using a replicated log. It's like a shared journal where every change to the database is meticulously recorded. All the nodes agree on the order of these changes, ensuring everyone has the same history.
So it's like a chronological record of every event. A single source of truth that all the nodes can refer to. Even if one node crashes, the others can use this log to rebuild its state and catch up to the latest version of the data.
Precisely. The replicated log becomes the bedrock of consistency, ensuring that even in the face of failures, the database remains unified and reliable.
That's brilliant. But I imagine managing a distributed log across multiple servers, especially with a high volume of changes, can be quite challenging. What are some of the hurdles and how are they overcome?
You're right. Maintaining a distributed log efficiently is no easy feat. Storage engines employ techniques like log compaction to keep the log size manageable, and efficient log propagation mechanisms to ensure changes are distributed quickly and reliably across the nodes. It's a whole area of research and development in itself.
It's amazing to think about all the intricate mechanisms working behind the scenes to ensure data consistency and reliability in distributed databases. It's like a well-coordinated dance, with each node playing its part in perfect harmony.
A beautifully orchestrated performance indeed. And beyond managing the log, distributed storage engines also need to tackle the complexities of data partitioning and query routing.
Right. Data partitioning is how you split the data across different nodes, kind of like dividing a large pie into smaller slices. But how do you decide which data goes where? Is there a method to this madness?
Absolutely. There are various partitioning strategies, each with its own trade-offs. One common approach is using a hash function to map data items to specific nodes.
So it's like assigning a unique address to each piece of data, telling the system exactly which server to find it on. That's a smart way to distribute the data evenly. But what happens when a user queries the database? How does the system know which node to contact to retrieve the relevant information?
That's where query routing comes into play. The system maintains metadata about the data partitioning scheme, essentially a map of the database. That guides queries to their destination.
So it's like having a GPS for your data, ensuring queries reach their destination quickly and efficiently. This whole system of data partitioning, query routing, replication, and consensus algorithms is truly remarkable. It's how distributed databases achieve scalability and reliability, handling massive amounts of data and user requests.
You've got it. It's a symphony of distributed systems concepts all working together to create a robust and powerful data management platform.
I'm starting to see the bigger picture here. Storage engines aren't just about storing and retrieving data. They're intricate systems designed to ensure reliability, consistency, and performance, even in the face of distributed complexities. They're the unsung heroes of the database world.
Precisely. They are the foundation upon which all database operations are built. And as our reliance on data continues to grow, the innovations in storage engine technology will only become more critical.
It's a field that's constantly evolving, with new challenges and exciting solutions emerging all the time. But before we get too carried away with the future, let's take a step back and revisit some of the fundamental concepts we've covered today.
That sounds like a great idea. Let's solidify our understanding of these building blocks before we venture further into the intricacies of distributed databases.
Okay, let's do a quick recap of what we've learned. We talked about how storage engines are like the foundation
of any database system, yeah.
They're responsible for storing, retrieving, and managing data.
Freeing up the DBMS to focus on those higher-level tasks.
We also discussed how the choice of storage engine can really impact database performance.
Absolutely.
In-memory systems offer that speed.
Blazing fast.
But they come with, cost considerations.
Right.
disk-based systems.
A little more practical for a wider range of applications.
Yeah. And we can't forget about data organization. Row-oriented systems are great at retrieving entire records. But column-oriented systems.
They shine when you're analyzing specific fields across those large data sets.
Exactly. It's all about choosing the right tool for the job. We dug into data files and index files, uncovered how B trees, with their unique design, ensure efficient data access.
And overflow pages.
Right. And we can't forget data integrity mechanisms.
Yeah.
Checksumming, transactions, concurrency control, all crucial for safeguarding the reliability and correctness of our data.
Absolutely.
We even touched on the complexities of distributed databases.
Where replication and consensus algorithms just work wonders.
It's incredible. I mean, this has been a wild ride.
It has.
Into this often hidden world of storage engines. It's amazing how much intricate engineering goes into something that we often take for granted.
It really is a testament to the computer scientists and engineers who have, dedicated their careers to building these robust or reliable systems.
Absolutely. So to all our listeners out there, the next time you interact with a database, whether it's booking a train ticket on IRCTC, ordering food online, even just scrolling social media.
Take a moment. Yeah.
To appreciate the storage engines working behind the scenes.
The unsung heroes of the digital age.
Quietly ensuring our data is stored safely, retrieved quickly, managed efficiently. And with that, we conclude our deep dive into the world of storage engines. Hopefully you enjoyed the journey, gained a newfound appreciation
for these fundamental components.
Absolutely.
Keep exploring. Keep learning.
And remember, there's always more to discover. Until next time. Hey everyone, and welcome back for another deep dive. We're going to be talking about database management systems today.
Sounds good.
Specifically, we're going to be looking at memory-based and disk-based systems. You're probably already pretty familiar with relational databases.
Right.
But, there's so much more going on kind of beneath the surface.
Yeah.
And I'm really glad to have you here to help kind of unpack this.
Right.
So let's dive right in. What are the fundamental differences between these in-memory and disk-based systems? Like, how do they actually use memory and disk?
Yeah, that's a great question to start with. And it's a common misconception that these systems exclusively use one or the other. Like, It's either all memory or it's all disk.
Right.
The truth is both in-memory and disk-based systems use both memory and e-disk.
Okay.
What differentiates them is how they primarily store and access data.
Okay, so it's more about where the data lives primarily.
Yeah, exactly.
Okay.
Exactly. So in an in-memory DBMS, as the name suggests, data primarily resides in the computer's RAM.
Okay.
This allows for blazing fast data access and processing speeds.
Right.
Disk storage, in this case, is mainly used for durability purposes. Think of it as a safety net.
Yeah.
So it's used for logging changes and creating checkpoints, ensuring that even if the system crashes, the data can be recovered.
So even with in-memory systems, we can't completely just disregard the disk.
Yeah, exactly. Disk-based structures are still very, very crucial, even in these high-speed systems.
Okay.
Now, shifting gears to disk-based DBMS, which is the more traditional approach, data primarily resides on the hard drive. Memory, in this case, is often utilized as a temporary storage space or a cache for frequently accessed data, aiming to speed up access times.
So you're saying that, like, a disk-based system, if it had like a really big cache, could achieve similar speeds to an in-memory system?
Not quite. That's where the aha moment comes in.
Okay.
You see, it's not simply about data location, but also about how it's structured and accessed.
Okay.
In-memory systems are designed from the ground up to leverage the speed of RAM.
Right.
They utilize specific data structures and techniques that just aren't possible or as effective when data originates on a disk.
So it's not just about throwing a big cache at the problem.
Exactly.
There's a fundamental difference in the approach.
Exactly. Yeah.
Okay. So where do these systems shine? And again, I'm kind of curious about this sort of like disk-based structures play a role in both these scenarios.
Yeah, you hit the nail on the head by highlighting the continued relevance of disk-based structures.
Yeah.
Let's start with in-memory systems.
Okay.
They truly excel in use cases that demand like lightning-fast processing. Think of real-time analytics, high-frequency trading where milliseconds matter, or fraud detection systems that need to analyze data instantaneously.
Right.
These systems can handle massive amounts of data, but their real strength lies in processing that data with incredible speed.
Yeah, I can definitely see why those use cases need that kind of speed. What about scenarios where in-memory systems act kind of as a caching layer.
That's another great example. In web applications, for instance, caching frequently accessed data in memory can significantly reduce the need to hit the much slower disk storage.
Right.
This leads to faster page loads and a better user experience. And remember, even in these scenarios, disk-based structures are working diligently in the background, ensuring data is saved and can be recovered if needed.
Yeah, it's amazing how even when data is primarily in memory, disk still plays such a crucial role.
Exactly.
So what about disk-based systems? Where do they kind of prove their worth?
Disk-based systems are champions when it comes to handling massive data sets, those that just wouldn't fit entirely in memory.
Right.
Think of managing financial transactions, customer relationship management systems, or inventory management for large companies.
Yeah.
These data sets can be truly enormous, and disk-based systems are built to handle that scale.
Right? Those data sets can be huge. So I'm guessing they also come into play when we talk about data that doesn't need to be accessed all the time, but still needs to be stored.
Absolutely. Disk-based systems are essential for archival and historical data.
Right.
This could be data required for compliance or auditing, or even data that might be useful for future analysis.
Right.
This type of data might not be accessed frequently, but it still needs to be stored securely and reliably.
Yeah.
And disk-based systems are perfectly suited for that purpose.
So we've established that disk-based structures are really crucial for both in-memory and disk-based systems.
Yes.
What I'm still kind of like hung up on is if they both utilize disk, what causes such a drastic difference in their performance?
The answer lies in the fundamental difference in data access speeds between memory and disk.
Right.
Accessing data in memory is lightning fast.
Right.
Orders of magnitude faster than retrieving it from disk.
Right.
Imagine trying to recall something you just learned.
Yeah.
Versus having to search for it in a massive library.
Okay, yeah.
Retrieving from memory is like instantly accessing that knowledge, while fetching from disk involves finding the right book, opening it to the correct page, and then reading the information.
Yeah, that's a good analogy.
Yeah.
So even though in-memory systems are incredibly fast, disk still matters because ultimately we need to be able to retrieve that data reliably and potentially store vast amounts of it.
You got it. Both systems employ clever techniques like logging and checkpointing to ensure data durability and consistency.
Right.
These mechanisms essentially act as safeguards, ensuring that even if an in-memory system suddenly loses power, it can recover its data from the disk and resume the operations from where it left off.
Wow, this is really eye-opening. All this complexity working behind the scenes just to make sure our databases are reliable and performant.
Exactly, and we're only scratching the surface here.
Right.
There's a whole fascinating world of concepts like B-trees, log-structured storage, and concurrency control, all playing a crucial role in database internals.
Wow. Okay, this is a lot to take in, but I'm definitely intrigued. It's amazing how much goes into making these systems work seamlessly.
Yeah, definitely.
Thanks for guiding us through this.
You're welcome.
So listeners, we've just begun our exploration of memory-based and disk-based database systems. We'll be right back after a short break to delve even deeper into this fascinating world. Don't forget to hit that like button, subscribe to the channel, and share this episode with your friends. We'll be back in a flash.
Welcome back, everyone. Before the break, we were talking about how that speed difference between accessing data from memory versus disk really influences the design and organization of data within these systems.
Yeah, it's like organizing tools in a workshop, right? Like if you've got everything within arm's reach on a small workbench, you'd arrange things differently than if you had a massive garage where you have to walk to different sections.
That's an excellent analogy. In memory, you can use more complex and interconnected data structures because you can jump around so quickly. On a disk, however, you need to be more deliberate, organizing data sequentially to minimize those time-consuming physical movements of the disk's read head.
So how do those B trees you mentioned earlier fit into all of this? How do they help organize data on disk?
B-trees are a fascinating example of how we've adapted data structures for efficient disk access. Imagine you have a database table with billions of rows.
Right.
Without an efficient search structure, finding a specific record could involve reading a huge portion of the data from disk, which would be incredibly slow.
Yeah, that doesn't sound efficient at all.
Yeah.
So how do B-trees solve this problem?
A B-tree is what we call a self-balancing tree structure. It automatically rearranges itself as data is added or removed to maintain a balanced structure.
Right.
And this balance is crucial because it ensures that the time it takes to search for a specific piece of data remains relatively constant even as the data set grows massively.
Okay, I'm starting to see the advantage here, but can you break down how this actually works? What makes B-trees so efficient?
Think of a B tree like an index in a book.
Okay.
It tells you exactly which page to go to for a specific topic. In a B tree, data is organized into nodes, and each node can contain multiple keys and pointers to other nodes.
So instead of reading through the entire database, the B tree acts as like a roadmap.
Exactly.
Leading you directly to the data you need.
Exactly. The B-tree structure is specifically designed to minimize the number of disk accesses needed to find a particular key. By keeping the tree balanced, we avoid scenarios where the search path becomes very long and requires lots of disk reads, keeping things snappy even with massive data sets.
That's really clever. It's all about minimizing those slow disk operations as much as possible.
What about cases where the data itself is larger than a single block on disk?
Excellent question. Remember, disks are divided into blocks?
And you can only read or write one block at a time. When we have data that's larger than a single block, we use something called overflow pages.
Overflow pages. So it's like adding extra sheets of paper when you run out of space on one.
That's a great way to visualize it. These overflow pages are linked to the original page, and the system knows how to follow these links to retrieve the complete data.
So even with the inherent limitations of disk storage, there are ways to manage large pieces of data effectively.
Absolutely. And it's not just about managing large data, but also about handling the constant changes to data over time.
Right.
Data gets updated, deleted, added. Yeah. It's a dynamic environment.
That makes sense. So what happens when data is deleted from the database? Doesn't that leave gaps and unused space on the disk?
You're right. Those gaps can lead to wasted space and inefficiencies. To address this, both in-memory and disk-based systems have mechanisms for what we call vacuuming or garbage collection.
Okay, so it's like defragging your hard drive, but for a database. Cleaning things up and making space.
Exactly. Vacuuming runs in the background, reclaiming unused space, and reorganizing data on the disk for optimal performance. It's one of many complex tasks these systems handle behind the scenes to keep things running smoothly.
It's incredible how much is happening beneath the surface. We've talked a lot about managing data on disk, but you also mentioned logging earlier. Could you explain more about that and how it contributes to data reliability?
Absolutely. Logging is a fundamental mechanism that ensures data durability and allows databases to recover from unexpected failures.
Okay.
Think of it like keeping a detailed journal of every change made to the database.
So every update, every deletion, every insertion, it's all recorded in this log.
Precisely. These log records are written sequentially, which is highly efficient for disk-based systems.
Okay.
The beauty of this is that if the system crashes before those changes are permanently written to the main data files, the log can be used to reconstruct the database state.
So it's like having an undo button for the entire database. Yeah. If something goes wrong, you can rewind and replay the changes.
You could say that. If a crash occurs, the system can use the log to replay all the changes made since the last consistent state, bringing the database back to a usable point. This is a crucial safety net for both in-memory and disk-based systems, even though their primary storage mechanisms differ.
Logging really highlights how important disk-based structures are for ensuring data reliability. It's like a safety net protecting our valuable information.
Exactly. And this is just one example of the intricate interplay between memory and disk in the world of database management systems.
This has been incredibly insightful. It's amazing how much complexity goes into making databases reliable and performant.
It certainly is a fascinating area.
We could probably go on for hours about all the intricate details.
Yeah.
But we're running out of time for today.
You're right. But we've covered some of the key differences between memory-based and disk-based DBMS and how each leverages memory and disk to store, access, and protect data.
Definitely. Before we wrap up, do you have any final thoughts for our listeners as they continue to explore this fascinating world of database systems?
I think the biggest takeaway is just understanding that neither memory-based nor disk-based systems are inherently superior.
Right.
It all comes down to choosing the right tool for the job.
Yeah.
Sometimes you need the raw speed of in-memory processing, and other times the sheer storage capacity of disk-based systems is essential.
It's not an either situation. It's about understanding the strengths of each approach.
Exactly. And keep in mind, we've only scratched the surface here. There's a whole ecosystem of factors that influence database performance and scalability, from the hardware they run on to the specific algorithms used for tasks like concurrency control and indexing.
Yeah, it sounds like there's always more to learn in the world of databases.
Absolutely. The field is constantly evolving. But hopefully our deep dive today has given you a solid foundation for further exploration.
Definitely. Before we sign off, here's something to think about. We talked a lot about how the speed of accessing data, whether from memory or disk, really impacts database performance. But what other factors beyond that choice do you think are crucial for making a database truly fast and efficient? Something to ponder as you continue your journey into this amazing world of data.
That's a great question to leave our audience with. The quest for optimized data management is an ongoing one.
Well, a big thank you to our expert for sharing all this knowledge with us.
Happy to be here.
And to all our listeners, thank you so much for joining us on this deep dive into the world of memory-based and disk-based database management systems. If you enjoyed this deep dive, don't forget to like, share, and subscribe to our channel for more enlightening deep dives into the world of technology. Until next time, welcome to the Deep Dive. Today, we're going to kind of unpack something you probably use every day without even realizing it. Databases.
Yeah.
Specifically, we're diving deep into how they actually store information.
Okay.
The difference between column-oriented and row-oriented systems.
That's a good one.
Yeah.
Yeah.
So you're already familiar with relational databases, tables, columns, rows, the whole shebang.
Yep.
But have you ever considered that the way this data is physically laid out on disk can make or break your database's performance?
Absolutely.
That's what we're getting into today.
Yeah, it's like the difference between having a well-organized library and a room full of randomly scattered books.
Oh.
One lets you find what you need quickly and efficiently, the other not so much.
Perfect analogy.
Yeah.
So let's start with the classic approach.
Okay.
Row-oriented systems.
All right.
Think of it like a spreadsheet.
Okay.
Each row represents a complete record.
Makes sense.
If you need all the details about a specific customer, like their name, address, order history, you fetch the entire row.
You got it.
So that's where row-oriented systems really shine.
Yeah.
When you need to access complete records quickly.
Right.
Think of online transactions, like booking a flight or making a bank transfer. You need all the information about that specific transaction together.
All in one place, yeah.
But what if you're only interested in specific pieces of information from a massive data set? Like imagine you're analyzing customer data and want to see the average age of customers in a particular city.
Okay.
Do you really need to fetch every single detail about each customer?
Yeah. That's where things can get a little less efficient.
Right.
You end up pulling in a lot of data you don't need just to get to those few specific fields.
Yeah.
It's like reading an entire book to find a single sentence.
Okay, so that's where column-oriented systems come into play, right?
Break say.
They flip the script entirely. Instead of storing data row by row.
Right.
They organize it by columns.
Like columns, yeah.
So all the ages would be stored together,
Yeah.
all the city names together, and so on.
Exactly.
So this has massive implications for performance.
It does. Yeah.
If you want to analyze customer ages or city distributions, you only need to access the relevant columns.
Exactly.
No need to sift through mountains of irrelevant data.
You got it.
It's like having a library where all the books on a particular topic are neatly shelved together.
I like that, yeah.
So if I'm doing a lot of analytical queries, crunching numbers, looking for patterns, column-oriented systems seem like the way to go.
Absolutely. They're specifically designed for those kinds of workloads.
Okay.
Think about analyzing website traffic, understanding customer behavior, or doing scientific research.
Yeah.
Any scenario where you're dealing with massive data sets and need to quickly analyze specific pieces of information.
But wait a minute.
Yeah.
If all the data for a single record is scattered across different columns, how do you reconstruct a complete record when you need it?
That's where the clever indexing and metadata comes in.
Yeah.
These systems use techniques to track where everything is stored and how it's connected.
Okay.
Think of it like a detailed map that tells you exactly where to find each piece of data and how to put it all back together.
So it's like having a jigsaw puzzle where each piece is a column.
Yeah.
And the database knows exactly how to assemble the complete picture.
Exactly. And the beauty of it is that you only fetch the pieces,
Right.
the columns
Yeah.
you actually need.
Okay.
You don't waste time and resources on the rest.
This is all incredibly fascinating.
It is, yeah.
It's amazing how much thought goes into something we often take for granted.
Absolutely.
But before we get too carried away with the conceptual stuff, let's get a bit more concrete.
Right.
Can you walk us through how these systems actually store and organize data on disk?
Of course. Let's start with slotted pages, a technique commonly used in both row-oriented and column-oriented systems.
Okay, so we've talked about row-oriented versus column-oriented systems in a general sense.
Right.
But let's get down to brass tacks.
Okay.
How does all of this actually work on a disk?
Yeah.
So you mentioned slotted pages earlier. What are those exactly?
It's basically just a way to organize data on disk efficiently. Yeah. Imagine a page as a container for data, like a page in a book. Right. And in a slotted page, this container is divided into, fixed size slots, each holding a pointer to a data record.
Okay.
This allows for managing data of varying sizes within that fixed size page.
So it's kind of like having a set of labeled boxes.
Yeah.
Each box is a slot.
Right.
And you can put whatever you want in there.
Yeah.
As long as you know which box it's in.
Exactly.
Okay.
This way, even if your data records are different sizes, you can still manage them efficiently within the confines of a fixed size page.
But what happens if a data record is too big to fit into a slot?
Yeah.
Does it get crammed in there anyway?
That's where overflow pages come into play.
Overflow pages?
If a data record is larger than a slot, it's stored on a separate overflow page.
Okay.
And the original slot simply holds a pointer to that location.
Oh, I see.
Think of it like having an extra storage room when your main closet is full.
So slotted pages and overflow pages help manage data efficiently.
Right.
But how do these systems actually find specific pieces of information quickly?
Yeah.
It seems like it would be a lot of searching if everything is scattered across different pages and slots.
Yeah, so that's where pointer hierarchies come in.
Pointer hierarchies.
These hierarchies establish relationships between keys and the actual locations of the data.
Okay.
Think of it as a multi-level index that guides you directly to the information you need without having to scan the entire disk.
So it's like having pointers to pages,
right,
and then pointers within pages to specific records.
Exactly.
It's a map within a map.
Precisely. These hierarchies, combined with clever search algorithms like binary search, enable databases to quickly pinpoint data on disk, even within massive data sets.
This is all incredibly efficient.
It is.
But what happens to the space occupied by deleted records?
Right.
Does it just sit there empty, taking up valuable disk space?
So not necessarily.
Oh.
When you delete a record, you essentially create a gap in the storage.
Okay.
Over time, these gaps can lead to fragmentation, which can impact performance.
Right.
To combat this, database systems employ processes like vacuuming.
Vacuuming. Like cleaning up the dust bunnies under the database rub.
Exactly. Vacuuming reclaims space occupied by deleted records and reorganizes the data to minimize fragmentation.
Okay.
This helps keep the database running smoothly and efficiently.
So vacuuming is kind of like defragging your hard drive.
Right.
But specifically for databases.
Yes, that's a good analogy. Okay. It's all about optimizing the physical storage layer for speed and efficiency.
Okay, so we've covered how data is stored and managed on disk.
Right.
But there's another crucial aspect of databases we need to talk about.
Okay.
Versions.
Yeah, versions are essential for managing concurrency and ensuring data consistency, especially when multiple users or applications are accessing and modifying the database simultaneously.
So it's like having multiple drafts of a document, each representing a different point in time, so you can see how it evolved over time.
That's a good way to visualize it.
All right.
In a version database, each update creates a new version of the record, rather than overwriting the existing one.
Yep.
This allows different transactions to work with different versions concurrently without interfering with each other.
Sounds complicated.
It can be.
Why go through all this trouble with versions?
Yeah.
What are the real-world benefits?
So imagine two people trying to book the last seat on a flight at the same time. Without versioning, one person might overwrite the other's booking, leading to confusion and potential errors.
Right.
With versioning, each person effectively works with their own copy of the data, ensuring that both bookings are handled correctly.
So versioning is like having a personal assistant for each user, ensuring they have the most up-to-date information without conflicting with others.
Exactly. Okay. It's all about managing concurrency and preventing data inconsistencies.
Right.
And it goes hand in hand with different isolation levels, which define how transactions interact with each other.
Okay, so versions and isolation levels work together to keep everything running smoothly.
Right.
But how do databases handle deleting data in a versioned environment?
Yeah.
Do deleted records just hang around forever, taking up space?
That's where the concept of tombstones comes into play.
Tombstones.
When a record is deleted in a version database, it's not actually removed immediately.
So we've been talking about tombstones. What happens when we delete stuff in these version databases?
Yeah.
It's not like hitting the delete key on your computer, is it?
No, it's a bit more nuanced than that.
Yep.
When you delete a record, it's not physically removed right away.
Right.
Instead, it's marked with a tombstone,
Okay.
a special marker that indicates the record is no longer valid.
So it's like putting a do not disturb sign on the Data's hotel room.
Yeah,
It's still there, but everyone knows it's out of commission.
precisely.
Okay.
This approach has several benefits.
Yeah.
For one, it simplifies concurrency control.
Right.
If another transaction tries to access that deleted record,
Yeah.
it sees the tombstone and knows not to proceed.
That makes sense.
Right.
But what about storage space?
Yeah.
If tombstones just sit there indefinitely,
Hmm.
wouldn't the database eventually become a graveyard of deleted data?
That's where garbage collection comes in.
Garbage collection.
Database systems have processes that periodically scan for tombstones
Okay.
and physically remove the associated data.
So they actually do get deleted eventually.
They do, yeah.
Yeah.
It's like a cleanup crew coming through and removing the abandoned hotel rooms, freeing up space for new guests.
So tombstones are a temporary measure to handle deletions gracefully,
Right.
and garbage collection takes care of the actual cleanup later on.
Exactly. This approach ensures data consistency,
Uh-huh.
simplifies concurrency control,
Right.
and manages storage space effectively.
Okay, so we've covered a lot of ground here.
We have.
Row-oriented versus column-oriented systems.
Right.
Storage techniques like slotted pages and overflow pages.
Yeah.
Planar hierarchies for efficient data access. And even the intricacies of tombstones and garbage collection.
It's been quite a journey into the inner workings of databases, hasn't it?
It really is. But before we wrap up, I have one more question for you.
Okay.
What advice would you give to someone who is trying to decide whether to use a row-oriented or column-oriented database for their application?
That's a great question. And it really depends on the specific needs of the application.
Okay.
If you're building an application that requires fast transactional processing,
Yeah.
like an online store or a banking system,
Right.
then a row-oriented database might be a good choice.
Okay.
But if you're building an application that requires complex analytical queries over large data sets,
Like data warehousing or business intelligence,
exactly.
then a column-oriented database might be a better fit. That makes sense.
Ultimately, the best way to decide is to carefully consider your application's requirements and choose the database system that best meets those needs.
This has been another incredible deep dive.
It has.
We've gone from the basic concepts of row-oriented and column-oriented systems all the way to practical advice on how to choose the right database for your application.
Absolutely.
Hopefully, this has given you a deeper appreciation for the power and flexibility of database systems.
It has for me, for sure.
We hope you found this deep dive insightful and engaging.
I-
If you did, please don't forget to like, share, and subscribe to the deep dive for more fascinating explorations of technology.
I will.
Until next time, keep on learning. Okay, so you're interested in getting like a deeper understanding of B trees, the backbone of so many databases that we all use every day. We're going to take a deep dive into how they're structured and how they're maintained on disk.
Yeah.
It's not like your typical file system. Think more like a super efficient library,
Right.
but built for speed.
Yes.
So that's kind of where we're going with this.
Yeah, what's so fascinating about B trees is that they're specifically designed to work with the way data is stored and retrieved from a disk.
Right.
We're talking about minimizing those really expensive disk reads, which can really, really bog down performance.
Right. So why not just use like a simpler binary tree?
Yeah.
Isn't that the classic way to organize data for searching?
It's true that binary trees are great for in-memory data,
Okay.
but when it comes to disk access, they can be quite inefficient.
Okay.
Imagine looking for a specific book in a library where each book is on a separate floor. That's essentially what happens with a binary tree on a disk.
Gotcha. So a B tree is like a well-organized library.
Yeah.
So what's the equivalent of like a book page then?
A B tree node is like a page in our library analogy.
Gotcha.
Each page has a header, like a table of contents,
Okay.
and cells that hold keys and pointers.
Right.
The keys are like the book titles guiding us to the right data, and the pointers are like the shelf locations.
Gotcha. I've heard about these high keys.
Yeah.
Are they like special VIP keys or something?
Not quite VIP, but they are important.
Okay.
The high key in a node is like the biggest book number in a library section. It helps us quickly determine if the data we're looking for is on that page, or if we need to move on to the next one.
Right.
Again, it's all about minimizing those disk reads.
Okay, that's really clever. So we've got pages and headers and cells and keys and pointers all working together to keep our data organized. But what happens if we run out of space on a page? Like trying to squeeze too many books onto a shelf.
Right. That's where overflow pages come in.
Okay.
Think of them as extra shelves in our library.
Mm-hmm.
When a page fills up, we create an overflow page and link it to the original page.
Right.
This allows us to accommodate a growing amount of data without sacrificing performance.
That's like adding an extension to the library.
Exactly.
And speaking of performance, how does all of this actually get stored on disk?
This is where things get really interesting.
Okay.
B trees are serialized,
Okay.
meaning the data is converted into a format that can be written to disk.
Okay.
It's like taking all those books and carefully packing them into boxes for storage.
Right, right. So the B tree structure itself has to be encoded in a way that the computer can understand.
Exactly.
Okay.
And the way the data is laid out on the disk, the page layout, is crucial for efficiency.
Mm-hmm.
Each page typically has a fixed size.
Right.
And within that page, we have the header, the cells with keys and pointers, and possibly links to overflow pages.
Okay.
It's all carefully designed to optimize disk access.
So even something as simple as the order in which we store things on a page can have a big impact on performance.
Absolutely.
Wow.
Even the smallest details matter when we're dealing with potentially massive amounts of data.
Yeah.
It's like organizing a library. If you don't do it right, it can take forever to find what you're looking for.
Right. Yeah. This is starting to make a lot of sense. So we've talked about how B trees are structured and stored on disk.
Yes.
But how do we actually find specific data within this massive organized library?
We still rely on our trusty binary search with some clever optimizations.
Yeah.
Remember those pointers we talked about? They act like shortcuts through our library, allowing us to jump to the right section without having to flick through every page.
Okay. So we're not just blindly searching through every book on every shelf.
Not at all.
Okay.
These pointers, called indirection pointers, help us navigate the tree much faster, minimizing those costly disk reads.
I'm starting to see how these B trees are the unsung heroes of database performance.
Yeah.
But databases are dynamic, right? New data is added, old data is deleted.
Right.
How does a B tree maintain its structure and efficiency through all of that change?
That's where things get even more interesting. B trees are designed to adapt to changes in data through operations called splits and merges. Think of it like reorganizing the library to accommodate new books and remove old ones.
So splits and merges are like the librarians working behind the scenes to keep everything organized.
Exactly. When a page gets too full with new data, we split it, like creating a new section in the library. Conversely, when pages become underutilized because of deletions, we merge them to keep things tidy.
It's like constantly optimizing the library layout for the best possible access. Are there other maintenance tasks that keep these B trees running smoothly?
Absolutely. Databases have processes called vacuum and maintenance that help keep things in tip-top shape. One issue they address is fragmentation.
Fragmentation. What does that mean in the context of a B tree?
Imagine a bookshelf where books are removed and added haphazardly, leaving gaps and making it harder to find things. That's fragmentation in a B tree. The data isn't nicely packed together, which can slow things down.
So vacuum and maintenance are like the librarians coming in and tidying up the shelves, making sure all the books are in their proper places.
That's a great analogy. These processes defragment pages, reclaim space from deleted records, and generally make sure the B tree is operating at peak efficiency.
It's amazing to think about all this happening behind the scenes every time we interact with a database. So we've covered the basics of B trees, but I've heard there are different flavors or variants of B trees. Why is that?
You're right. One size doesn't fit all when it comes to data management. Different applications have different needs and performance requirements. Some might be heavy on writes, others on reads, and some need to handle lots of users accessing data concurrently.
So it's like having different types of libraries for different purposes. A research library, a public library, a children's library, each with its own way of organizing things.
Precisely. Let's look at some of these B tree variants and how they address specific challenges. Take FD trees, for instance. They're designed for scenarios with lots of writes, like logging user activity on a busy website.
So if a regular B tree is like a traditional library, what makes an FD tree different?
Think of an FD tree as a library with a special buffer zone where new books are temporarily stored before being shelved. This buffer allows the FD tree to batch write operations, reducing the number of times it has to access the disk.
So it's like taking notes before filing them away, more efficient than making constant trips to the file cabinet. What about situations where you have lots of people trying to access the data at the same time?
That's where B trees come in. They're designed for high concurrency. Think of a busy library with multiple librarians all trying to access the cart catalog at the same time.
Boo trees, is there a story behind that name?
It stands for buzzword trees. But jokes aside, they're incredibly clever. B trees use special techniques like half-split nodes to avoid those librarian traffic jams.
Half-split nodes. That sounds intriguing.
Imagine a section of the library that's being reorganized, but instead of closing it off completely, they put up a section under construction sign while still allowing people to browse the books. That's kind of what a half-split node does. It allows other operations to continue accessing data even while a node is being split.
So it's all about maximizing access and minimizing disruption, even during those reorganization periods. Are there any other B tree variants that stand out?
Absolutely. LSM trees are real rock stars when it comes to handling write-heavy workloads. They're like a library that receives a massive delivery of new books every day.
So how do they deal with that influx of new data? Do they try to shelve everything immediately?
That would be incredibly inefficient. Instead, LSM trees use an append-only approach, like stacking those new books at the end of the shelves and sorting them out later.
So they prioritize getting the new data stored quickly and then worry about organizing it later.
Exactly. This avoids constant reshuffling and makes writing new data super efficient. Later, a process called compaction merges and sorts those new entries into the existing B tree structure.
It's like having a dedicated team of librarians working behind the scenes to keep everything organized without disrupting the flow of new books coming in.
That's a perfect analogy. This approach is especially beneficial when dealing with massive amounts of data, like in log files or data streaming applications.
It's fascinating to see how these different B tree variants have evolved to tackle specific data challenges. It makes you realize that even something as seemingly simple as storing and retrieving data involves a lot of clever engineering.
It's true, and what's even more fascinating is that the evolution of these data structures is driven by the ever-changing demands of data storage and processing. As we generate more and more data set, new challenges emerge, leading to even more innovative solutions.
It seems like there's always something new to learn in the world of databases.
Absolutely, and by understanding the fundamentals of B trees and their variants, you're well equipped to explore these new developments and appreciate the ingenuity behind them.
This has been an incredible journey through the world of B trees. I feel like I've learned so much about how these fundamental data structures power so much of what we do with computers.
Yep.
It really is. And it's easy to kind of take these things for granted, not realizing the complexity that goes into making our databases so fast and reliable.
Yeah, absolutely. But what we've explored today gives you a deeper appreciation for what happens under the hood. The next time you're searching for information or making changes to a database, think about that B tree or its variant working tirelessly behind the scenes to fulfill your request.
Yeah, it's like having this whole team of expert librarians constantly working to make sure the library runs perfectly.
Right.
Even though we only see the end result.
Exactly. And that's really the key takeaway here. The performance of your database isn't magic. It's the result of careful design and these incredibly clever data structures working tirelessly behind the scenes.
And by understanding how these structures work, we can make more informed decisions about, database choices, optimizations, and even how we design our applications.
It's all about empowering you, the listener, with the knowledge to navigate the complex world of data.
This has been an incredible deep dive into the world of B trees and their variants.
Yes.
I feel like I've learned so much about how these fundamental data structures power so much of what we do with computers.
Me too. And I hope you, the listener, have enjoyed this exploration of the hidden world of data structures.
Absolutely. And if you found this deep dive helpful, be sure to share and subscribe to our channel for more fascinating explorations into the world of technology.
We're always looking for new areas to explore and uncover those hidden gems of knowledge.
Until next time, keep learning, stay curious, and remember that even the most complex systems are built on fundamental principles waiting to be discovered. All right, welcome to another deep dive. I think we all know and love our relational databases.
Yeah.
But let's face it, we usually kind of stay at that SQL level. Today, we're going beyond the comfort zone a little bit and looking at how those databases, how they actually arrange themselves on disk.
Yeah, it's a whole different world down there.
Right.
When you think about it, you've got these fixed size blocks of disk space, and then you have data that can be all over the map in terms of size, names, text blobs, you name it.
So right off the bat, that's kind of a puzzle, right?
Yeah.
How do you fit something that's constantly changing size into a container that's fixed?
That's a great question.
Yeah.
And that's where the slotted page format comes in.
Okay.
So imagine you've got a page, kind of like a sheet of paper in the database world.
Right.
Now, instead of writing data directly onto this page, we divide it up into slots.
Okay, so like pre-marked sections or something.
Exactly. But here's the twist. Each slot doesn't hold the actual data. It holds a pointer.
Okay.
Which is a little address that tells the database where to find the real data somewhere else on that page.
Oh, so it's like you've got the table of contents at the top, and then the actual story is kind of scattered throughout the page.
That's a great way to put it.
Okay.
And the beauty of this is now you can have a short name like Tom.
Right.
Taking up just a little space right after a longer name like Ashwara.
Sure.
Without needing to shuffle everything around.
Right.
The pointers keep track of it all.
This is really making me rethink how I visualize data storage in my head.
Yeah.
But wouldn't searching through this become a nightmare? Like, it's not neatly ordered anymore, right?
And that's where the real cleverness comes in.
Okay.
The pointers themselves are actually sorted. So even though the actual data might be jumbled on the page, the database can use a super fast search algorithm on the pointers to find exactly what it needs in a snap.
So it's like having a sorted index. But instead of leading to a whole page, it's leading to a specific spot on the page itself.
Precisely.
Wow.
And this has a huge impact on performance, especially when you're doing lots of inserts, updates, or deletes.
Right.
Because instead of shifting these big chunks of data around, you're just rearranging those lightweight pointers.
I'm starting to see how all this, like, attention to detail
really
adds up at the low level.
Right.
But this is just within a single page, right? What happens when you've got, an entire database to organize?
Well, that's where our old friend the B tree comes into play.
Oh, yeah. Everybody loves B trees.
But with a disk-centric twist.
Okay.
We're used to thinking of trees, growing downwards from a root.
Right.
B trees on disk are built from the bottom up.
Okay.
With the leaf nodes, the ones holding the actual data, forming the base.
So flipping the script.
Kind of, yeah.
Why that bottom-up approach for databases?
Well, remember, disks are all about accessing data in blocks.
Right.
So having that most frequently accessed data, those leaf nodes, closer together makes retrieval much faster.
So it's like
organizing your bookshelf so the books you read the most are all within easy reach.
Yeah, that makes sense.
Yeah.
But wouldn't a single node in this B tree eventually, fill up?
Absolutely.
If you keep adding data?
Yeah, and that's where overflow pages come in.
Okay.
So think of it like needing extra shelves for your books, right?
Gotcha.
When a node gets too full, it links to another page.
Okay.
And that page becomes part of the structure.
So the B tree stays intact, just with a little, side room added on.
Exactly, a little extension.
Yeah. Okay, so we've got these pages, they're slotted, they're organized into a B tree, all cleverly arranged for disk access. What else is there to consider down at this level?
Well, one thing that might surprise people is how much metadata is tucked away in these structures.
Absolutely.
Each page usually has a header, like a label, containing information about its size, what kind of page it is, even things like checksums to ensure data integrity.
So it's not just data.
No.
There's like a whole system of organization built in.
Right.
That's interesting.
And one of the most interesting pieces of metadata is the high key.
High key?
You know how B trees use keys to guide searches?
Yeah, like deciding which branch to take down the tree, right?
Well, the high key is like a signpost at each node saying, the highest key you'll find in my subtree is this.
Oh, that's interesting.
So it lets the database quickly bypass whole sections of the tree.
Right.
If the search key is outside that range.
So it's like a shortcut for the search algorithm.
Exactly.
Yeah.
And all of these little optimizations add up to make databases the workhorses that they are.
This is really blowing my mind, the level of detail that goes into something that we just take for granted.
Right.
Like we just assume that it works. But there's so much thought and engineering that has gone into it.
And we haven't even touched on things like fragmentation and database maintenance.
All right, hold on. You're going too fast for me before we jump into those.
Okay.
Let's take a moment for our listeners to digest all of this awesome info.
Sounds good. So before the little break there,
Yeah.
we were kind of admiring all these intricate systems databases use to keep data organized on disk.
Right.
But this neat and tidy picture, it kind of gets a bit messy when we bring in the real world, right?
Well, that's what I was thinking. Like,
Yeah.
we're constantly adding, deleting, changing things.
Yeah.
All this perfectly arranged data.
Yeah.
It can't stay that way forever, right?
You're absolutely right. Think
How?
about it. You delete a record,
Yeah.
it leaves a gap.
Right.
You update something, it might take up more space or less space than before.
Right.
And over time,
Yeah.
our neatly slotted pages
Yeah.
and optimized B tree,
Hmm.
they start to fragment.
Fragmentation. So like when my hard drive gets all cluttered and slow.
Very similar concept.
Okay.
In a database, fragmentation means you've got these gaps and spaces
Yeah.
scattered throughout your pages and nodes.
Right.
Searching becomes less efficient
Right.
because the database has to kind of jump around more.
So how do databases deal with this? Is it like, a digital decluttering session?
Yeah, you could say that.
Okay.
The process is often called vacuuming,
Vacuuming. Okay.
and it happens behind the scenes.
Right.
The database goes through, identifies those empty spaces, and compacts the data
Okay.
to reclaim that lost space.
So like squeezing out all the air pockets,
Yeah.
making everything nice and tight again.
Exactly.
Okay, but wouldn't this constant vacuuming slow things down?
It's a balancing act, right?
Yeah.
Vacuuming does take some resources,
Yeah.
but letting fragmentation get out of hand would hurt performance even more in the long run.
Right.
So databases are smart about when and how to do this cleanup to minimize disruption.
Makes sense. Little maintenance goes a long way.
Yeah.
Are there any other tricks that databases use to keep things running smoothly on disk?
Oh, absolutely.
Okay.
One we haven't touched on yet is compression.
Okay.
Remember how we talked about page headers containing metadata?
Uh-huh.
Well, some databases use those headers to signal whether the data on that page is compressed.
Wait, so they're actually shrinking the data itself to save space?
Yeah.
How does that work without losing information?
Well, there are tons of different compression algorithms out there,
Right.
each with its own trade-offs.
Sure.
Some are better for text, others for numbers.
Yeah.
But the basic idea is to find patterns and repetitions in the data
Uh-huh.
and represent them in a more compact way.
So instead of storing Aishwarya, Aishwarya, Aishwarya 3 times,
Right.
it's like finding a way to say Aishwarya times 3?
You got it.
Okay.
And then when the database needs to read that data, it decompresses it on the fly.
This is blowing my mind again.
Yeah.
So we've got this whole hidden world of compression and decompression happening,
Mm-hmm.
all to make our databases faster and more efficient.
It's remarkable how much optimization goes into something as fundamental as data storage.
Yeah.
And we've honestly just scratched the surface here.
I'm almost afraid to ask, but what other tricks do these clever database developers have up their sleeves?
Well, remember those pointers we talked about in the slotted page format?
Yeah.
There's another layer of cleverness there that we haven't explored yet.
Oh, boy.
Imagine you need to move a piece of data to a different location on the page.
Okay.
Maybe because you updated it and it now takes up more space.
All right. So you need to rearrange things a bit.
Right.
But doesn't that mean updating all the pointers that point to that data?
That's where indirection pointers come in.
In direction pointers. Okay.
It's a bit of a mind bend.
Right.
But instead of the slots pointer directly leading to the data,
Uh-huh.
it leads to another pointer, and that one points to the actual data.
Wait, so a pointer to a pointer.
Exactly.
Why add that extra step?
Think of it like this.
Okay.
You've got a signpost pointing to your favorite restaurant.
Okay.
Now imagine the restaurant moves across the street.
Right.
Instead of moving the signpost, which would be a lot of work,
Yeah.
you just change the direction it's pointing to.
Oh, I see.
Right.
So by adding this extra layer,
Yeah.
if the data moves, you only need to update that one indirection pointer.
Right.
Not all the pointers in the slot.
Exactly. It's a small change with a big impact on efficiency.
Right.
Especially when you're dealing with lots of updates and data reorganization.
Yeah.
And this kind of cleverness is everywhere in database implementations.
This has been an amazing journey so far.
Yeah.
From those slotted pages to compression algorithms.
Yep.
And even pointer tricks.
Uh-huh.
I'm starting to appreciate the complexity behind something.
Yeah.
As seemingly simple as just storing data. But I have a feeling we're not done yet, right?
Know it. There's so much more to discover.
Right.
Especially when we start talking about how these concepts scale to massive data sets
Wow.
and distributed systems.
Right.
But for now,
Yeah.
let's give our listeners a moment to soak in all this new knowledge.
Okay, we're back. And my head is still spinning from all those database storage secrets.
Yeah.
It's like we peeked behind the curtain and realized there's this whole world of intricate machinery keeping things running.
It really is amazing.
It is.
The ingenuity of those database developers
Yeah.
constantly pushing the boundaries of efficiency and performance.
And as you said, we've only just scratched the surface here.
Yeah, just a little glimpse.
But even with this little glimpse, I feel like I'm looking at databases in a whole new way.
That's what's so cool about these deep dives right there. It opens up a whole new way of thinking about these things.
Totally.
We use every day.
And for someone who uses databases every day, like this knowledge is super empowering.
Oh, absolutely.
You know? It's like learning how your car engine works.
Right.
You don't need to be a mechanic.
Yeah.
But understanding can help you diagnose problems.
Absolutely.
Make smarter choices.
Yeah.
Appreciate the complexity of what's going on.
I like that analogy.
Yeah, you know. And it's the same with databases.
Right.
When you understand how that data is physically laid out on disk, you start to see why certain queries are faster.
Yeah.
Why indexing is so important.
Right.
How different configurations can impact performance.
It all comes together.
Yeah. It's like those slotted pages.
Yeah.
Now I understand why inserting a new record is so much faster than it used to be when I was just thinking about data as these abstract tables.
Those abstract concepts.
Right, exactly.
And remember, B trees, knowing how they're structured on disk can help you design your database schema in a way that minimizes those disk scenes of data retrieval.
This deep dive has really given me a lot to think about.
Me too.
You know? It's not about memorizing facts.
Right.
It's about connecting the dots.
Yeah.
Seeing the bigger picture.
Absolutely.
Of how everything works together.
And that's what makes this stuff so fascinating, right?
Yeah, totally.
There's always more to learn.
Yeah.
New technologies emerging.
Right.
Always new challenges to solve.
I'm definitely feeling inspired to keep exploring.
Yeah, me too.
And I bet our listeners are too.
I hope so.
So for those of you who want to dive even deeper,
yeah,
we've got some great resources linked in the show notes.
As always.
And as always.
We encourage you to like, share, and subscribe to The Deep Dive.
So we can keep bringing you these explorations.
Into the world of technology.
Thanks for joining us on this journey.
Yeah, thanks for listening, everybody.
Into the depth of database storage.
Until next time.
Keep that curiosity alive.
Keep diving deep.
And we'll see you on the next Deep Dive. All right, welcome back, everyone. Today we're going deep on something that's, well, pretty fundamental to how we use data every day. But most of us probably don't give it a second thought.
Yeah, it's one of those things that just works until it doesn't, and then it's a huge EE problem.
Exactly. We're talking about the magic that makes your data reliable, specifically in relational databases.
Think about online shopping, banking. Anything where data accuracy really matters, like you want to be sure that when you order something, it actually goes through and you're not charged twice, right?
Absolutely. Correct. Or that your bank balance is correct after you deposit a check. So what's going on behind the scenes to make sure all of this works flawlessly?
It all comes down to something called transaction processing. And trust me, it's way more interesting than it sounds.
Okay, I'm intrigued. So transactions, like when I buy something online, is there more to it than just a simple click and done from the user's perspective?
Way more. Behind the scenes, a transaction is an entire sequence of operations. Like, imagine transferring money between bank accounts. It's not just one action. It's debiting one account, A&D crediting the other, all while making sure nobody can spend that money twice in the middle of the process.
Oh, I see where this is going. The database has to treat this whole set of actions as one unit, right? Either everything succeeds or everything fails.
You got it. This is the first A-city principle, atomicity. It's like that old saying, all or nothing.
Okay, atomicity, got it. So what are the other A-city properties that keep our data safe?
Well, there's consistency. It's kind of the rule follower. Make sure that a transaction always takes the database from one valid state to another, like a good citizen.
So what does that mean in a practical sense?
Let's say your bank has a rule that you can't withdraw more money than you have in your account. Consistency makes sure that any transaction, like a withdrawal, respects that rule and doesn't leave your balance negative.
Makes sense. Each transaction is kind of like its own little bubble, making sure everything inside is valid before it becomes official.
Exactly. Great way to put it. And then there's isolation. Imagine 100 people trying to book the last seat on a flight all at the same time. Chaos.
Oh, yeah. Definitely a recipe for disaster.
Well, isolation ensures that each of those transactions acts as if it's the only one happening. This prevents all sorts of mix-ups and ensures data accuracy, even when things get really busy.
So isolation is all about preventing chaos and making sure everyone gets a fair shot at that last seat. What about that last letter D?
Durability. It's the save button of the database world. Ensures that once a transaction is committed, its changes are permanent, even if the system crashes or the power goes out. Think of it like your guarantee that once you complete a purchase online, that order is saved and won't disappear, even if the website has a hiccup.
That is reassuring. So we've got atomicity, consistency, isolation, and durability AC. Now, we know these ACD properties are essential for reliable data management, but what's actually going on behind the scenes? How do databases pull off this magic?
It's a bit like a well-choreographed dance, and there are two key players: buffer management and lock management.
Okay, I'm ready to learn these dance moves.
Great. Let's start with buffer management. You know how you keep your most frequently used tools handy for quick access? Databases do the same thing with data. They use a buffer, also called a page cache, in memory to hold frequently accessed data pages, speeding up operations.
So it's all about keeping the important stuff readily available for faster processing. Makes sense. But what happens when the buffer gets full? Do they just start randomly discarding data?
Of course not. That would be disastrous. Databases use clever algorithms to manage the buffer, like the least recently used, or LRU, algorithm. It keeps track of what's being used, and if the buffer gets full, it evicts the page that hasn't been touched in the longest time, making space for new ones.
So it's out with the old, in with the new. But what if that old data is suddenly needed again?
Well, then the database fetches it back from disk, which takes a bit longer. Choosing the right buffer management strategy is a delicate balancing act for good performance.
Okay, buffer management keeps things organized and efficient. That makes sense. What about lock management? What's its role in this dance?
Lock management prevents clashes. Imagine multiple people trying to edit the same document at the same time. Chaos.
Yeah, I can see how that would get messy fast.
Well, databases use locks to control access to data and make sure transactions don't step on each other's toes. It's like putting a temporary under construction sign on a data item while a transaction is working on it.
So locks act like traffic signals, directing the flow of transactions and preventing collisions.
Precisely. Buffer management and lock management work together to ensure data integrity and, you guessed it, support those all-important AC properties we talked about.
Wow, that's a lot more going on behind the scenes than I ever imagined. And it all works so seamlessly that we rarely even notice it as users. But what about when things go wrong? When the system crashes or there's some kind of error, how does the database recover and make sure our data is still accurate?
That's where the concept of recovery processes comes in. We'll dive deeper into that in the next part of our deep dive.
So we've talked about these behind-the-scenes mechanisms that make ACD properties work: buffer management and lock management. But like you said, what happens when things go wrong? Systems crash, errors pop up. How does the database recover and ensure our data is still accurate?
That's where the concept of recovery processes comes into play. And a critical component here is the write-ahead log, or WAL for short. Think of it like a super detailed journal that records every change made to the database before those changes are actually applied.
So it's like a safety net, a record of everything just in case.
Exactly. Now, when the database restarts after a crash, it uses the WAL to replay those journaled changes. This process brings the database back to a consistent state, restoring any committed transactions that occurred before the crash.
So it's like rewinding and replaying a recording to get back to where you left off.
Yeah.
Pretty clever. But replaying the entire WAL every time seems like it could be pretty time-consuming, right?
You're absolutely right, and that's where checkpointing comes in. Periodically, the database takes a snapshot of its current state and saves it to disk. During recovery, the database only needs to replay changes from the WAL that occurred after the most recent checkpoint, making the process much faster.
So checkpointing is like creating bookmarks in the database's journey. Smart. We touched on the LRU algorithm for buffer management earlier, but are there other ways databases decide what to keep in memory?
Absolutely. Not all data is created equal. Some data is more critical, and databases use various algorithms and strategies based on factors like the type of data, how frequently it's accessed, all sorts of things.
Okay, so it's not just a one-size-fits-all approach. What are some examples of how databases might prioritize certain types of data?
For instance, index pages, which help quickly locate specific data, often get higher priority in the buffer because they're so crucial for query performance.
It's like making sure the library catalog is always readily available, even if some books are temporarily out of reach.
A perfect analogy. And remember, all these processes, buffer management, lock management, recovery, become even more intricate when we move to the world of distributed databases, where data is spread across multiple machines.
Distributed databases. Now that sounds like a whole other level of complexity, which actually makes you appreciate all the intricate work that goes on behind the scenes just to ensure that our data is accurate and reliable. Ready to dive into the world of distributed databases?
Let's do it.
All right, we're in the final stretch of our deep dive here. We've covered how databases ensure data integrity on a single system. But now things get really interesting as we step into the world of distributed databases. I can only imagine the complexity of maintaining those ACD properties when the data is spread across multiple machines.
It definitely adds a whole other layer of challenges. Imagine you have data on servers all over the world, and a single transaction needs to update information on multiple servers. How do you ensure atomicity in that scenario?
Yeah, that sounds incredibly complicated. It's like trying to coordinate a dance with dancers in different countries. How do distributed databases manage to pull that off?
One common approach is the two-phase commit protocol. It's like a carefully choreographed dance where a coordinator server leads the participant servers through the steps of the transaction.
So there's a central leader making sure everyone is in sync. What are the steps involved in this dance?
Well, in the first phase, the coordinator checks in with all the participants asking, "Are you ready to commit this transaction?" If everyone gives the green light, they move to the second phase where the coordinator instructs everyone to commit the changes.
It's like a double check system to make sure everyone is on the same page before making those changes permanent. But what happens if one of the dancers misses a step? What if a participant fails to commit or the coordinator itself crashes?
That's a great question. Distributed systems are definitely more prone to these kinds of hiccups. So these protocols need to be very robust. In the two-phase commit, if a participant can't commit, the coordinator instructs everyone to abort the transaction. It's like hitting the undo button to ensure everything stays consistent.
So even with those potential issues, the system is designed to maintain that data consistency. That's impressive. But what about recovering data after a crash in this kind of distributed environment? That seems like a whole other puzzle.
It is. When a server in a distributed database crashes, you need to recover the data on that server and make sure it's consistent with the rest of the system. Distributed databases often rely on replication, keeping multiple copies of the data on different servers.
So it's like having backup dancers ready to step in if someone falls.
Exactly. And they use a distributed write-ahead log, which keeps track of changes across all servers. This ensures that those replicas stay in sync.
So even with crashes and potential errors, distributed databases have these mechanisms in place to maintain data integrity. It's kind of mind-boggling how much complexity is involved.
Absolutely. It's a real testament to the ingenuity of those who design and build these systems, constantly innovating to ensure our data is safe and reliable.
Well, I think we've covered a lot of ground today, from the fundamental concepts of ACD properties to the intricacies of distributed databases. It's been a fascinating journey.
We've only scratched the surface, but hopefully you have a deeper appreciation for how databases keep our data consistent and reliable.
I definitely do. Big thanks to you for guiding us through this deep dive. Listeners, if you want to explore this topic further, be sure to check out the show notes for links to some excellent resources.
And don't forget to like, share, and subscribe to The Deep Dive.
We'll be back soon with another fascinating topic. Until then, keep those aha moments coming. All right, let's jump into a deep dive on something super important when you're working with those massive data sets, especially for all of you in India. We're talking buffer management and cache eviction strategies. They might not be the most glamorous part of databases, but man, they can make or break performance.
Yeah, you got it. When you're dealing with huge amounts of data, efficient retrieval is everything. It's like keeping that traffic flowing smoothly on a busy highway, you know? You don't want any data bottlenecks.
So let's start with the basics. What exactly is buffer management? What's the big deal?
Okay, think of it like this. Buffer management, it's kind of like the middleman between your database storage, usually on a hard drive, and the rest of your system. It basically grabs the data you use a lot and keeps it handy in memory.
Oh, okay, so it's like keeping your favorite tools within reach instead of digging through a toolbox every time you need them.
Exactly. But here's the thing. Memory isn't unlimited, right?
Right. So what happens when the cache is full? How do we make space for new stuff?
That's where these cache eviction strategies come in. They decide which pages to kick out, just like deciding which tool you use least to make space in your toolbox.
Okay, interesting analogy. So what are some of these strategies? How do they work?
Well, you've got simple ones like FIFO, first in, first out. It just evicts the oldest page in the cache.
So kind of like cleaning out your fridge and tossing the oldest stuff first.
Yeah, sort of, but it's not always the most efficient because you might toss out something you actually use a lot.
Right, that makes sense. So is there a smarter way to choose what to evict?
Definitely. There's LRU, or least recently used. It keeps track of when each page was last accessed and evicts the one that's been gathering dust the longest.
Okay, so like assuming that if you haven't used an ingredient in a while, you probably won't need it anytime soon.
Exactly. But even LRU has its limitations, especially in India, where you have such diverse and large user bases. Data access patterns can be really unpredictable.
Right. So what do we do then? How do we deal with that unpredictability?
That's where these even more advanced algorithms, like CLOCK sweep and tiny LFU, come into play.
Ooh, fancy names. Tell me more.
Well, CLOCK sweep is like a modified version of LRU. Think of it as a two-step process. It checks if pages have been used recently and gives them a second chance to stay in the cache. Only if a page hasn't been used in a while, it gets evicted.
Oh, so it's like a stay of execution for those pages. I like it.
Yeah.
But what about this tiny LFU? How does that one work?
Tiny LFU is totally different. It's almost like it has a crystal ball. It tries to predict what data you'll need next based on past usage.
Well, hold on. So it's not just reacting to what's been used. It's actually trying to predict the future.
Yep, that's the idea. And this can save you precious milliseconds on each query, which really adds up when you're handling millions of records.
Yeah. Okay, that sounds pretty amazing. So is that like the best option then, especially for large data sets in India? Tiny LFU.
Well, it can be really powerful, but it's also more complex. It really depends on a lot of factors, like the type of data you have, the performance you need. There's no one-size-fits-all answer, unfortunately.
Okay, that makes sense. So all these different algorithms, how do they actually impact performance, especially with all those input-output operations going on?
Think about it this way. When the database needs data that's not in the cache, it has to go to the hard drive, which is way slower. That's what we call a disk I/O operation. It's like a traffic jam on our data highway.
Yeah, so avoiding those I/O operations is key, right? Especially with those huge data sets you guys are working with in India.
Exactly. A good cache eviction strategy keeps the data you need most readily available. That means faster retrieval, faster query processing, and overall a much more responsive system.
This is fascinating stuff. Really shows how much is going on behind the scenes to make these databases work smoothly.
For sure. And for anyone in India working with large databases, understanding all this can give you a serious advantage. Choosing the right strategy can really be the difference between an application that flies and one that crawls.
Well said. So we've talked about the basics, but I want to dive a bit deeper into how these algorithms work. You mentioned that CLOCK sweep gives pages a second chance. Can you break that down for us? How does that actually work in practice?
Sure. Imagine all the pages in your cache arranged in a circle, kind of like a clock face. And each page has a little hand pointing to it. When a page is accessed, its hand moves to show that it was recently used. And then an algorithm kind of sweeps around the clock, looking for pages whose hands haven't moved in a while.
So it's like musical chairs for data pages, with the least recently used ones getting kicked out. But wouldn't this still miss out on pages that might be needed soon, even if they haven't been accessed recently?
That's a good point. And that's where tiny LFU shines. Instead of just looking at recent access, it tries to predict future access patterns. It looks at how often each page has been used in the past.
So it's like a data historian, learning from past use to make better predictions about the future. That sounds incredibly powerful, especially when dealing with those massive data sets we often see in India. Can you give us an example of how this might play out in a real-world scenario?
Okay, imagine an e-commerce app in India. It has a huge product catalog. Some products, like mobile phones or things related to festivals, might be super popular during certain times of year. Tiny LFU can learn these patterns and proactively keep those data pages in the cache, even if they haven't been used recently.
Wow, so it's like anticipating a shopping rush and stocking the shelves of the hottest items. That would make things so much faster for users.
Absolutely. Especially when things are busy, those milliseconds really matter. Tiny LFU can really make the user experience better by making sure the data they want is ready to go.
This is all making me think about how important it is to choose the right strategy. What are some of the things we should consider when making that decision?
You got to think about your workload. Is it mostly reading data or writing data? Are the access patterns predictable or all over the place? How big is your data set? What kind of performance do you absolutely need? All these things matter.
Sounds complicated. Are there any other practical tips we should keep in mind when we're putting these strategies into action?
Yeah, remember that cache eviction strategies are just one part of the puzzle. The size of your buffer pool, how efficient your locking mechanisms are, the overall setup of your database, they all affect how well your strategy works.
Okay, so it's not just picking the coolest algorithm, it's about understanding how everything works together.
Exactly. You need to know your database environment and your workload really well. It's about tweaking all the little things to get the best balance of performance, efficiency, and using your resources wisely.
That makes a lot of sense. Now, let's shift gears a bit and talk about those disk I/O operations you mentioned before. Can you explain why there's such a big bottleneck, especially when we're talking about huge data sets in India?
Well, disk I/O operations are basically when the database has to physically read data from the hard drive or write data to it. And those operations are way, way slower than accessing data from memory. It's like the difference between walking to your neighbor's house and flying across the country.
Gotcha. So every time the database has to go to the hard drive, it's a big performance hit.
Right. And that hit gets even bigger when you're dealing with the massive data sets that are common in India. We're talking millions, maybe even billions of records. Every trip to the hard drive adds milliseconds, which can quickly add up to noticeable delays for your users.
And those delays can be really annoying for users, especially in apps where speed is super important.
Exactly. Imagine you're using an online banking app in India. If you have to wait several seconds just to see your account balance because the disk I/O is slow, you're going to get frustrated. You might even switch to a different bank.
Yeah, no one wants to deal with that. It really shows how these technical details can have a real impact on people's experiences.
Exactly. We often think of databases as these abstract things, but they're actually serving real people who care about how well they perform.
So optimizing these behind-the-scenes processes is crucial. It's about making sure our apps can provide a smooth and responsive experience, even when dealing with huge amounts of data.
That's the goal.
This makes me wonder about the role of hardware. We've been talking about hard drives, but what about newer technologies like solid-state drives?
Yeah.
Those are much faster, right?
Yeah. SSDs are game changers for storage. They use flash memory instead of spinning disks, so they're way faster at reading and writing data. It's like trading in your bicycle for a sports car.
So if we're using SSDs, do we still need to worry about optimizing disk I/O as much?
SSDs definitely help, but they don't completely solve the problem. Accessing data from memory is still way faster than from storage, even with SSDs.
Right, so it's still important to keep that frequently used data in memory.
Yeah, even with the speed of SSDs, the sheer volume of data in large data sets means optimizing those data access patterns is still crucial.
That brings up another interesting point. We've been talking about single databases, but what about those distributed systems where data is spread across multiple machines? How does all this apply in those situations?
Great question. That takes us into the world of distributed caching, which is a whole other beast. In a distributed system, you have to think about not just what data to cache, but also where to cache it.
Oh, I see. So it becomes even more complex.
Definitely. You need to consider both the access patterns and the physical location of the data. There are all sorts of techniques and algorithms to handle that, like consistent hashing and distributed locking.
Sounds like a topic for another deep dive.
It definitely is. It's really interesting how database technology keeps evolving, always with new challenges and opportunities.
Before we move on, is there anything else about buffer management that you think our listeners should keep in mind, especially those who are working with those large data sets in India?
One thing I'd emphasize is the importance of monitoring your database's performance. Even after you've picked the best cache eviction strategy, you need to keep track of things like cache hit ratios, I/O wait times, and query response times.
So it's not just a set it and forget it kind of thing.
Nope, you gotta keep an eye on things and fine-tune your system to make sure it's running its best. By watching those metrics, you can spot potential problems and make adjustments.
Great advice. Well, we've covered a lot of ground on buffer management and cache eviction strategies.
Yeah.
I think our listeners have a much better understanding of how important these concepts are now.
I hope so. It's all about making those databases work smarter, not harder.
Exactly. And it's especially relevant for all of you working with those massive data sets in India. Optimizing your database performance can make a world of difference. Now, before we wrap up this deep dive, I want to leave our listeners with a question to ponder. We've talked about all sorts of factors that influence how well a cache eviction strategy works. But what about the data itself? How does the structure of the data, how it's organized, and the relationships within the data, how does that affect the performance of these algorithms?
That's a really interesting question. The way data is structured definitely plays a role in how it's accessed. And that, in turn, affects which pages are kept in the cache. For example, if related pieces of data are stored close together, they're more likely to be accessed together. That can lead to more efficient cache utilization. But if the data is scattered all over the place, it can lead to more cache misses and slower performance.
So it's not just about the algorithm, it's about how we organize and store our data as well.
Exactly. It's about making sure all the pieces fit together to build a system that performs at its best.
Well said. We've explored buffer management, cache eviction strategies, and even touched on the impact of data structure. This deep dive has given our listeners a lot to think about and apply to their own work with databases.
I agree, and I encourage everyone to keep exploring these topics. The world of databases is always changing, with new challenges and opportunities popping up all the time.
Absolutely. So to our listeners, especially those of you working with those large data sets in India, remember that optimizing database performance is an ongoing journey. Keep experimenting, keep learning, and keep pushing the boundaries of what's possible.
Well said.
And that brings us to the end of part 1 of our deep dive into buffer management and cache eviction strategies. We'll be back soon with part 2, where we'll dig even deeper into the intricacies of these algorithms. So make sure you stay tuned. And in the meantime, don't forget to like, share, and subscribe to The Deep Dive for more explorations of the tech world. Until next time, keep those curiosity gears turning.
See ya then. It's like this. Each page has a little flag, and when a page is accessed, the flag is set. The algorithm sweeps through the cache, and if it finds a page with its flag set, it means that page was used recently, so it gets to stay. But if the flag isn't set, the page is a candidate for eviction.
Ah. So it's like a little checkpoint.
Yeah.
If the page hasn't been used recently enough to have its flag set, then it's out.
Exactly.
But that still doesn't solve the problem of potentially evicting a page that might be needed soon, even if it hasn't been used in a little while.
Right, and that's where tiny LFU comes in. Instead of just looking at whether a page has been used recently, it tries to figure out how frequently a page is used overall.
So it's not just about recency, it's about popularity too.
Exactly.
So like if a page is accessed a lot, even if it hasn't been used in the last few minutes, tiny LFU will recognize that it's still important.
Exactly.
Fascinating. So KLOC Keep is like checking attendance, and tiny LFU is keeping track of grades.
That's a great way to put it.
So to bring this back to our listeners in India, let's imagine we're building a system to handle, say, train ticket bookings.
Okay, I'm following you.
During peak travel seasons, certain routes or trains become super popular.
Right, like during Diwali or Holi.
Exactly. Now with tiny LFU, even if a particular route hasn't been booked in the last few minutes, the system will remember that it's generally a popular route and keep that data handy.
Exactly. So when someone searches for that route, the system can respond quickly, even if there's a sudden surge in demand.
Wow, that's impressive. It's like the system is anticipating what users will need before they even ask.
That's the power of predictive algorithms like tiny LFU.
So it seems like choosing the right cache eviction strategy is crucial for building responsive and efficient applications.
Absolutely. Especially when you're dealing with large-scale systems and unpredictable user behavior.
Okay, so let's say we're tasked with choosing a cache eviction strategy for a new system.
Okay. What do we need to consider?
What are some of the key factors that should influence our decision?
First, you need to understand your workload. Are you dealing with mostly read operations or write operations?
So like, is the system primarily used for retrieving data, or is it frequently updating data as well?
Exactly. Then think about the access patterns. Are they predictable or do they change a lot?
I see. So like in our train booking example, we know there will be predictable spikes in demand during certain times.
Right. But in other applications, the access patterns might be more random.
And then, of course, there's the size of the data.
Right. How much data are you actually dealing with?
And finally, what are your performance requirements? How fast does the system need to be?
Exactly. You need to consider all of these factors to choose the strategy that's going to work best for your specific situation.
It's like finding the perfect recipe. You need to get all the ingredients right.
Exactly.
Now, before we move on, are there any other practical considerations that we should keep in mind?
One thing to remember is that the cache eviction strategy is just one part of the overall system.
Right, we can't just focus on the algorithm in isolation.
The size of your buffer pool matters. The efficiency of your locking mechanisms, the overall configuration of your database, all these things play a role.
So it's about understanding how all the pieces fit together.
Exactly. It's about fine-tuning the entire system to achieve the optimal balance of performance, efficiency, and resource utilization.
Now let's talk about something we touched upon earlier. Disk I/O operations.
Okay, what about them?
Can you elaborate on why they're such a major bottleneck, especially when we're talking about those massive data sets that are common in India?
Sure. Remember, disk I/O operations involve physically reading or writing data to a hard drive, and these operations are much, much slower than accessing data from memory.
So every time the database has to go to the hard drive to get data, it's a huge performance hit.
Exactly. And the more data you have, the bigger the problem becomes.
So for our listeners in India who are often dealing with enormous amounts of data, optimizing disk I/O is critical.
Absolutely. Minimizing those trips to the hard drive can make a world of difference in terms of application performance.
Now, this makes me think about the role of hardware.
Okay, what about it?
We've been focusing on hard drives, but what about newer technologies like solid-state drives or SSDs? Those are supposed to be much faster, right?
SSDs are a game changer when it comes to storage performance. They use flash memory instead of those spinning platters and hard drives, so they're much faster for both reading and writing data.
So if we're using SSDs, does that mean we don't have to worry about disk I/O as much?
SSDs definitely help a lot, but they don't completely eliminate the issue. Even with SSDs, accessing data from memory is still significantly faster than reading it from storage.
So it's still about minimizing those trips to storage, even if they're much faster with SSDs.
Exactly. And when you're dealing with the volume of data we often see in India, those small differences in access time can really add up.
So optimizing data access patterns remains crucial, even in a world with SSDs. This brings up another interesting point. We've been talking about single standalone databases, but what about distributed database systems? Where the data is spread across multiple machines.
Right. What about them?
How do these concepts of buffer management and cache eviction apply in that scenario?
That's a great question. And it takes us into the world of distributed caching.
Ooh, sounds complicated.
It can be. Now we have to think about not only what to cache, but also where to cache it across all those different machines.
So it becomes a multi-dimensional problem.
Exactly. You need to consider both the data access patterns and the physical location of the data.
And I'm guessing there are a whole bunch of new algorithms and techniques to deal with this.
You got it. Things like consistent hashing and distributed locking come into play.
It sounds like that's a topic for another deep dive.
It definitely is, but it just goes to show that database technology is constantly evolving.
Always something new to learn. Now, before we wrap up our discussion on buffer management, is there anything else you want to emphasize for our listeners?
One thing I'd stress is the importance of monitoring your database's performance. It's not enough to just choose a caching strategy and forget about it.
So what should we be monitoring?
You want to keep an eye on things like cache hit ratios. That tells you how often the data you need is already in the cache.
And what about I/O wait times?
Exactly. That's how long your system is waiting for data to be read from or written to storage.
And of course, we need to be tracking query response times.
Exactly. That's how long it takes for your database to respond to a request for data.
So monitoring these metrics can help us identify any potential bottlenecks.
Absolutely. And then you can fine-tune your system to address those bottlenecks.
Great advice. It seems like optimizing database performance is an ongoing process.
It definitely is. It's not a one-time fix. It's about continuous improvement.
Well, we've covered a lot of ground today. We've talked about buffer management, cache eviction strategies, the impact of disk I/O, and even touch upon the world of distributed caching.
It's been a great discussion.
Our listeners, especially those working with those large data sets in India, have a lot to think about now.
I hope so. These concepts are crucial for building high-performing database systems.
Absolutely. So stay tuned for part 3 of our deep dive, where we'll explore even more advanced topics in database optimization. So we've learned a ton about how these algorithms work and what to consider when choosing one. But I want to circle back to something you mentioned earlier about the impact of data structure. You said how the way data is organized can affect the performance of these algorithms. Can you expand on that a bit?
Sure. It all comes down to how the data is accessed. If related data is stored together, it's more likely to be accessed together, right?
Right. So like if we're talking about customer data, all the information about one customer should be stored together.
Exactly. And if that's the case, then those related pieces of data are more likely to end up in the cache at the same time, which means fewer trips to the hard drive and faster performance.
So it's not just about choosing the right eviction strategy. It's also about optimizing the way the data is stored in the first place.
Absolutely. It's all connected.
And this is especially important for our listeners in India who are dealing with those massive data sets.
For sure. When you have that much data, even small optimizations can make a big difference.
It's like optimizing the flow of traffic in a huge city.
Exactly. You need to make sure everything is organized and flowing smoothly.
Well, I think we've covered a lot of ground today. We've gone deep into the world of buffer management, explored different cache eviction strategies, and even touched upon the impact of data structure. It's been a fascinating journey.
It really has.
And I hope our listeners have gained some valuable insights that they can apply to their own work with databases.
Me too. Remember, optimizing database performance is an ongoing process. It's all about continuous improvement.
Couldn't have said it better myself.
Yeah.
So to our listeners, keep experimenting, keep learning, and keep pushing the limits. And that brings us to the end of our deep dive into buffer management and cache eviction strategies. A big thank you to our expert for sharing their insights.
It was my pleasure.
And to all of you listening, thank you for joining us. Don't forget to like, share, and subscribe to The Deep Dive for more explorations of the tech world. Until next time, keep those curiosity gears turning. Welcome back, everyone, to another Deep Dive. You know, we love to go deep and really explore some fascinating concepts in tech and data. And today we're going to be talking about log-structured storage, or LSS for short.
Sounds pretty intense.
It is pretty cool stuff, actually. It's all about making databases faster, especially when you're dealing with tons of writes. I mean, think about it. We're generating mountains of data here in India these days. So making sure those databases can keep up is a big deal.
Yeah, that makes sense. I'm already interested.
Sure.
So where do we start?
Well, I think the best place to start is with you. You're the expert here. Can you give us a quick rundown of what exactly log-structured storage is? I mean, we all know about relational databases and B trees, but how is LSS different?
Right. So think of it like this. Imagine you're keeping a logbook or a diary. You just keep adding new entries one after the other, always at the end. That's basically what LSS does. It appends new data sequentially to a log file.
Okay, so instead of like constantly rearranging a library every time we get a new book, it's more like just stacking newspapers on top of each other.
Exactly. And that seemingly simple difference makes a big difference when it comes to speed, especially write speed. Because with LSS, all you're doing is adding to the end of the log. No need to reorganize anything.
Makes sense. So writes are super fast. But doesn't that mean the log file just keeps getting bigger and bigger? How does LSS handle that?
That's where log compaction comes in. It's like taking that stack of newspapers you mentioned and tidying it up every now and then. You get rid of old newspapers, maybe combine similar ones into neat bundles. That's what log compaction does. It cleans up the log by merging and removing unnecessary information.
So it's like a digital decluttering process, keep things neat and manageable.
Yeah.
But I'm guessing this compaction thing happens in the background, right?
Yeah, it does. It runs as a separate process, so it doesn't slow down the writes.
That's good.
Yeah.
Makes sense.
Yeah.
But hold on, if we have this huge log file, even if it's compacted, how do we actually find specific information within it? Do we have to read the whole thing?
Well, that wouldn't be very efficient, would it? That's where some really clever techniques come in, and that's what we'll get into next.
All right, so we've got this massive log file, constantly growing, even with compaction going on. How do we actually find specific information within all that data?
Well, it wouldn't be very efficient to just read through the entire log every time, right?
Yeah, I figured there had to be a better way.
Exactly.
Better.
LSS systems use some really smart techniques, a combination of indexing and these things called probabilistic data structures to make reads fast and efficient.
Indexing, I get probabilistic data structures. That sounds a bit more complicated.
Don't worry, it's not as complex as it sounds. So one of the key techniques is using what's called a keydir.
Keydir, like a key directory.
Sort of. Think of it like an index in a book. It tells you where to find specific information within the log.
Okay, so instead of flipping through every page of our newspaper stack, we can just check the keydir and know exactly where to look. Makes sense.
Exactly. And to speed things up even further, we use Bloom filters.
Bloom filters. Okay, now you're really losing me.
Imagine you're looking for a book in a library, but instead of searching every shelf, you first check the library catalog. The catalog tells you if the book even exists in the library, right?
Yeah, I see where you're going with this.
So a Bloom filter is like that catalog. It tells you if the data you're looking for might be present in a specific part of the log.
Might? So it's not always accurate.
It's highly accurate, but it's probabilistic. So there's a tiny chance it could give you a false positive.
Meaning it might say the data is there when it's actually not?
Exactly. But the speed boost you get from eliminating unnecessary searches is well worth that small risk.
Interesting. So it's all about optimizing for speed, even if it means sacrificing a little bit of accuracy in some cases.
Exactly.
This is really fascinating. It sounds like LSS has some serious advantages, especially for applications where you're doing a lot of writes.
Ah.
But I'm guessing there are some trade-offs, right? Nothing's perfect.
You're right. Every system has its strengths and weaknesses. And with LSS, the main trade-off is that reads can be a bit more complex compared to traditional B trees.
Because you might have to scan multiple parts of the log and deal with different versions of the data.
Exactly.
So writes are a breeze, but reads might require a bit more work.
Is there a way to think about this trade-off more formally, like a framework or something?
There is. It's called the RIM conjecture.
What, RIM conjecture? Okay, that sounds interesting.
It stands for read, update, and memory overhead. It basically helps you understand the costs associated with different storage systems.
So with LSS update, costs are low because writes are fast, but read costs might be a bit higher.
Got it.
RAM conjecture. I'll have to remember that. So it's all about choosing the right tool for the job, weighing the pros and cons based on what your application needs.
Exactly.
Now, all this technical stuff is great, but I'm curious, how does this actually play out in the real world? Can you give us some examples of where LSS really shines?
Sure. Think about applications that deal with massive amounts of data and need to handle a lot of writes or updates, things like sensor data financial transactions or user activity on a massive scale. So systems that need to keep up with a constant stream of new information.
Exactly. Those are the scenarios where LSS can really outperform traditional systems.
Makes sense. So it's not about replacing B trees altogether, but recognizing that LSS offers a powerful alternative for certain use cases.
Precisely.
Now, you mentioned certain use cases. Can you give us some concrete examples of systems that actually use LSS, systems that our listeners might have heard of?
Absolutely. Systems like RocksAB, Cassandra, and HBase, they all leverage log-structured storage to achieve high write throughput and scalability.
Wow, so this stuff is actually being used in real-world applications.
Oh, yeah. They're used everywhere, from managing large data sets to powering real-time analytics platforms.
That's really cool. It's amazing to see how these seemingly abstract concepts translate into actual technology that we use every day. This deep dive has been super insightful. We've gone from the basics of LSS all the way to its real-world applications. But before we wrap up, I have one last question that I think will really get our listeners thinking. You know, we've talked a lot about how LSS is all about immutability. Data never gets changed in place. It just gets added to the log. And it got me thinking, could this idea of immutability be useful outside of databases too?
That's a really interesting thought. And it makes sense when you think about the benefits of immutability. Things like auditability, version control, and making things easier to manage when multiple processes are accessing the data at the same time.
Right. Like with blockchain technology, immutability is a big part of what makes it work.
Exactly. It's definitely something worth exploring further.
It's amazing how these concepts from the world of databases can have such a broad impact. It just shows you that innovation often comes from connecting ideas from different fields. So before we let you go, any final thoughts on LSS for our listeners?
I think the key takeaway is that LSS is a really powerful approach to data storage, especially when you're dealing with lots of writes. If you're working with data-intensive applications, particularly here in India, where we're seeing such a surge in data, LSS is definitely something to keep on your radar.
Absolutely. And if you're looking for specific systems to explore, RocksDB and Cassandra are great examples of LSS in action.
Yeah, those are good ones.
This has been another fantastic deep dive. I always learn so much from these conversations.
Glad to hear it.
And for our listeners, I hope you learned something new today too. If you enjoyed this deep dive, don't forget to like, share, and subscribe to the deep dive for more fascinating explorations into the world of data and technology. Until next time, keep exploring. Welcome to the deep dive. Today, we're going to be taking a look at distributed systems. And you know, a lot of you out there work with relational databases. So we're going to try to break down some of these concepts using things that you're already familiar with.
Yeah, we're going to be focusing on the abstractions.
Okay.
The big ideas that make these systems work.
Abstractions.
You know, so think about it like
Yeah.
understanding like the blueprints of a city.
Okay.
You don't need to know the exact layout of every building to get a sense of how the city functions as a whole.
Okay, I like that.
Yeah.
So when we talk about distributed systems,
Yeah.
what is the fundamental difference compared to a relational database?
So in a relational database, everything is in one place.
Right.
It's like a well-organized library where all the books are in a single building.
Okay.
But in a distributed system, the information is spread out across multiple nodes, like having different libraries scattered across the city.
Okay, so if the data is spread out, how did these different nodes work together?
Yeah.
It can't be a free-for-all. Right.
Absolutely not. Just like a city needs a transportation system to connect different areas, distributed systems rely on communication to function.
Right.
And this is where the concept of cooperation comes in.
Cooperation, okay.
Each node needs to be able to talk to others, share information, and coordinated actions.
So it's like each library having a special delivery service to exchange books and keep track of what's where.
That's a great way to think about it. The primary way these systems communicate is through something called message passing.
Okay.
Think of it like sending emails or memos between different departments in a company.
Makes sense.
Yeah.
But I can imagine things getting messy with messages flying around everywhere.
Yeah.
What happens if a message gets lost or delayed or even duplicated?
Yeah, you've hit on a crucial point.
So.
Those are some of the biggest challenges in distributed systems.
Yeah.
Just like in real life, communication isn't always perfect. Messages can get lost in the network, arrive late due to congestion, or even be duplicated.
So how do these systems cope with such unreliable communication? Do they have any backup plans?
They do. Distributed systems are designed to be resilient. They use various techniques to ensure that messages reach their destination and that any hiccups don't disrupt the system's overall function.
Okay, so we've got the communication part down.
Yeah.
But let's say a node has some new information that it needs to share.
Right.
How does that information spread efficiently across the entire system?
That brings us to the concept of dissemination.
Dissemination.
Think of it like spreading news or updates across a large organization.
Right.
You wouldn't want to rely on one person to tell everyone individually, right?
Right, that would take forever and probably end up like a game of telephones, like message getting distorted along the way.
Distributed systems need clever ways to spread information quickly and reliably.
Right.
One fascinating approach they use is called gossip protocols.
Gossip protocols.
Yep.
That sounds like something straight out of a high school drama.
It might sound informal.
Yeah, but it's actually a powerful technique.
Okay.
It's based on the idea that nodes share information with their immediate neighbors, who then share it with their neighbors, and so on.
Yeah.
Just like how news or rumors can spread organically through social networks.
Oh, so it's like a chain reaction of information sharing.
Yes.
But how can they be sure everyone gets the message if each node only knows a limited number of other nodes?
That's the beauty of gossip protocols.
Okay.
They work even when each node only has a partial view of the network.
Right.
It's like you might only know a handful of colleagues in a large company, but through them, you can still hear about important news or updates that originated from a completely different department.
Wow. That's really clever.
Yeah.
So even with limited connections, the information can spread throughout the whole system.
That's right.
But I have another question.
Sure.
If there's no central authority, how do these distributed systems make decisions? It's like trying to get a group of friends to agree on where to eat. It can be a nightmare. That's a great question. This is where the concept of consensus comes in. Consensus is crucial in a distributed system because it allows a group of nodes to agree on something despite the lack of a central command center.
So it's like having a voting system.
Yeah.
Where nodes need to reach majority agreement before taking action.
You got it. One common way to achieve consensus is through leader election.
Leader election. Okay.
Just like a group might choose a captain or leader, distributed systems can elect a node to make decisions on behalf of the whole group.
But I can imagine that choosing a leader in a system with so many nodes and with communication being somewhat unreliable, it must be quite challenging. What if the chosen leader suddenly goes offline?
Exactly. Leader election in a distributed system comes with its own set of hurdles.
Right.
What if a leader fails?
Right.
How do you ensure a smooth transition of power? These are all problems that distributed systems need to address.
It sounds like there's a lot more going on behind the scenes than I initially realized. This whole idea of coordinating actions across so many nodes without a single point of control is fascinating.
It is, and we're just scratching the surface here.
Okay.
There are so many more fascinating aspects to distributed systems, from how they handle timing and order of events to the challenges of keeping data consistent across all the nodes.
Well, I'm definitely hooked.
Great.
This has been an eye-opening start to our deep dive into distributed systems.
Yeah.
I'm eager to learn more about how they tackle these complex challenges.
Stay tuned, because we're just getting started.
Before we move on, let me remind all our listeners to like, share, and subscribe to The Deep Dive for more fascinating explorations into the world of technology. We'll be back after a short break with part 2 of our deep dive into distributed systems.
See you then.
Welcome back to The Deep Dive. Before the break, we were talking about how distributed systems cooperate, spread information, and even manage to make decisions without a central authority. But I'm curious about something we haven't touched on yet.
Okay. Oh, yeah, that's a really important point. In a relational database, everything happens in a nice, orderly sequence because it's all in one place.
Right.
But in a distributed system, things can get a little bit tricky.
Right, because messages are traveling across networks.
Yeah.
Nodes might be processing information at different speeds.
Right.
It's like trying to coordinate a project with team members scattered across different time zones.
Exactly.
You can just assume everyone is on the same page at the same time.
Exactly. And this is where the concept of synchrony versus asynchrony comes in.
Okay.
In a synchronous system, everything moves in lockstep.
Okay.
Like a well-rehearsed dance routine.
Right.
Each step depends on the previous one, and there's a clear, predictable order of events.
So a synchronous system is like a scheduled meeting where everyone knows exactly when to show up and what to discuss.
Precisely.
Uh-huh.
But in an asynchronous system, things are a bit more free-flowing. Messages can be delayed, nodes might work at different speeds, and there's no guarantee that events will happen in a specific order. It's more like sending emails back and forth. You never know exactly when someone will reply or if they'll see your message immediately.
So asynchronous systems sound a bit chaotic. How do they manage to get anything done if there's no clear order of events?
It's a challenge, but distributed systems have clever ways of dealing with it. For example, they use timestamps and sequence numbers to help track the order of messages and ensure that actions are executed in a consistent way, even if things arrive out of order.
That makes sense. It's like putting a date and timestamp on your email so you can reconstruct the conversation even if messages arrive out of order. But I'm still trying to wrap my head around this idea of nodes working independently and at different speeds.
Yeah.
It seems like that would make it really difficult to keep track of the overall state of the system.
You're absolutely right.
Yeah.
This is one of the biggest hurdles in distributed systems managing what we call shared state.
Shared state.
Imagine you're collaborating on a document with colleagues.
Right.
But everyone has their own copy and makes changes independently.
Yeah.
Keeping those copies synchronized and ensuring everyone has the latest version can quickly become a nightmare.
Oh, I've definitely been in that situation before. Yeah. It's so frustrating trying to figure out who made what changes.
Yeah.
And which version is the correct one.
Exactly. And in a distributed system with data spread across multiple nodes, the challenge of shared state becomes even more complex.
Right.
There's no single source of truth.
Right.
So the system needs ways to ensure that all nodes have a consistent view of the data, even if they're working with slightly outdated information.
So it's not just about getting messages from point A to point B. It's about making sure those messages result in a synchronized and coherent view of the data across the entire system.
Absolutely. And this brings us to the concept of consistency models, which define how and when updates to the data are reflected across different nodes.
Okay, consistency models sound important.
They are.
Can you tell me more about how they work and what kinds of choices developers have to make?
There's a whole spectrum of consistency models, each with its own trade-offs.
Right.
Some prioritize strong consistency, guaranteeing that all nodes see the same data at the same time.
Okay.
This is like having a live shared document where everyone sees updates in real time.
Okay, that sounds ideal. But I imagine there must be a downside.
Right.
It seems like achieving that level of consistency in a distributed system would require a lot of coordination.
Yeah.
And could potentially slow things down.
You're exactly right. Strong consistency can be expensive in terms of performance, as it requires constant communication and synchronization between nodes.
Right.
That's why some systems opt for weaker consistency models,
right,
where updates might take some time to propagate across all nodes.
So it's a bit like choosing between a live video call where you see everyone's reactions in real time, versus sending a text message where there might be a delay before everyone gets the message.
That's a great analogy. The choice of consistency model depends heavily on the specific needs of the application.
Right.
For some applications, like banking systems, strong consistency is absolutely critical.
Yeah, to avoid errors.
Right, to avoid errors and inconsistencies.
Like inconsistencies.
But for others, like social media feeds, eventual consistency where updates eventually reach all nodes might be sufficient and allow for better performance.
This is all starting to make a lot more sense.
Good.
It's fascinating to see how distributed systems have to balance these competing demands of consistency, availability, and performance.
And we're just getting started. We've talked about how nodes cooperate, how they spread information, and how they grapple with issues of timing and shared state. But one of the most crucial aspects of distributed systems is how they handle failures.
Oh, that's a good point.
Yeah.
After all, in a system with so many moving parts, things are bound to go wrong from time to time. What happens when a node crashes or a network connection goes down? It seems like that could bring the whole system to a halt.
That's where the concept of fault tolerance comes in. Distributed systems are designed to be resilient and keep functioning even when things go wrong.
Okay, fault tolerance sounds like a must-have.
It is.
But how do they actually achieve that?
One of the key techniques is replication.
Right.
Which essentially means creating backup copies of the data and distributing them across multiple nodes.
So if one node goes down, the system can just switch over to a backup.
Exactly. But replication introduces its own set of challenges.
Okay.
How do you make sure all those copies stay consistent? How do you handle updates when some copies might be temporarily unavailable?
Right.
These are just some of the questions we'll be exploring as we delve deeper into the world of fault tolerance in distributed systems.
This is getting more and more intriguing. I'm starting to see how many layers of complexity there are in building and managing these systems.
And we're only just scratching the surface. But don't worry, we'll guide you through it all, step by step.
Well, I can't wait to hear more. Before we continue, a quick reminder to our listeners, if you're enjoying this deep dive into distributed systems, don't forget to like, share, and subscribe to the deep dive for more insights into the world of technology. We'll be back after a short break to continue our exploration. Welcome back to the deep dive. We've been talking about how distributed systems handle some pretty complex challenges, from coordinating actions to maintaining data consistency. But before we wrap up, I'm really curious about one more thing we briefly touched upon earlier, fault tolerance.
Yeah, fault tolerance is absolutely crucial in distributed systems.
Okay.
After all, we're talking about systems with multiple nodes, network connections, and all sorts of components that can potentially fail.
Right.
It's like having a car with multiple engines. If one engine fails, you want the car to keep running.
That's a great analogy.
Yeah.
So how do these systems ensure that they can keep going even when parts of them fail?
One of the key techniques is replication, as we mentioned earlier.
Right.
It's like having backup copies of your important files stored in different locations.
Right.
If one copy gets corrupted or becomes inaccessible, you still have others to rely on.
Okay, so replication provides redundancy.
Yes.
But how do these systems manage all those replicas? It seems like it would be easy for things to get out of sync, especially when you consider the communication challenges we discussed earlier.
You're right. Managing replicas effectively is one of the biggest challenges in distributed systems.
Okay.
We need to ensure that updates are applied consistently to all replicas, even if some are temporarily unavailable.
Right.
And we need to handle situations where replicas might have conflicting information due to network issues or other failures.
Right. That sounds like a real headache.
Ah.
Are there any specific strategies or techniques they use to tackle these replication challenges?
There are several. One approach is to use a primary backup replication scheme.
Okay.
In this setup, one replica is designated as the primary, and all updates are first applied to it.
Right.
These updates are then propagated to the backup replicas.
Yeah.
It's like having a master copy of a document with multiple backup copies for safety.
So it's a clear hierarchy.
Yeah.
The primary replica is the source of truth, and all others follow its lead.
Exactly. This simplifies things in terms of consistency,
Right.
as we only need to worry about keeping the primary replica up to date.
Right.
But it also introduces a single point of failure.
Right.
If the primary replica goes down,
Yeah.
the system needs a way to elect a new primary and ensure a smooth transition.
That makes sense. But what if we want to avoid having a single point of failure? Are there other replication approaches that offer more resilience?
Absolutely. Another approach is peer-to-peer replication,
Okay.
where all replicas are considered equal.
Go.
Updates can be applied to any replica, and they are then propagated to the others. This is more like having multiple collaborators working on the same document, with changes being merged and synchronized.
Okay, that sounds more flexible and resilient, but I imagine it must be more complex to manage.
Yeah.
How do they ensure consistency when any replica can be updated?
You're right. Peer-to-peer replication requires more sophisticated mechanisms to handle concurrency and conflicts.
Right.
We need to make sure that updates are applied in a consistent order across all replicas, even if they arrive out of order or if there are concurrent updates happening at the same time.
So it's like having a group of people editing the same document simultaneously,
Yeah.
but with clever algorithms to make sure the final version is coherent and reflects everyone's changes.
Exactly. There are various techniques such as conflict resolution algorithms and distributed locking mechanisms that help ensure consistency in peer-to-peer replication.
Wow. It's amazing how distributed systems can handle such complex scenarios and still maintain a coherent view of the data.
Yeah.
It's like a well-choreographed dance with all these nodes working together despite the potential for chaos.
It is, and that's why understanding these concepts, these abstractions, is so important. It allows you to appreciate the challenges involved in building and managing distributed systems and to make informed decisions about the trade-offs between consistency, availability, performance, and fault tolerance.
I have to say, this deep dive has been incredibly enlightening.
Yeah.
It's given me a whole new appreciation for the complexities of distributed systems and the ingenuity of the solutions they've come up with.
It's a fascinating field, and we've only just scratched the surface.
Yeah.
There's so much more to explore and learn about distributed systems.
Well, I'm definitely eager to continue this journey of discovery. And for our listeners who are equally intrigued, I encourage you to like, share, and subscribe to The Deep Dive for more fascinating explorations into the world of technology. Until next time, keep those minds curious and those learning gears turning. Okay, get ready to dive deep, because today we're tackling distributed systems.
Oh, this is a fun one.
It is. Think those massive relational databases, but spread across multiple computers.
Ah, interesting.
How do they handle failures and keep running smoothly, even with, well, chaos? That's our deep dive today.
You know, in distributed systems, failure isn't a question of if, it's when. Hardware crashes, networks act up, software has bugs.
Yeah, it's a digital jungle out there.
Absolutely, it's a jungle.
So just like a city needs backup power and routes during emergencies, distributed systems need ways to cope with failures.
Right. That's a great analogy.
So first, how do they even detect those failures? Imagine computers happily working and one goes offline.
Right.
How do the others know it's gone?
Good question. It's like, a group text where friends are checking in, someone goes silent, maybe they're busy, their phone died,
Yeah.
Similar here. We use something called heartbeats, those regular check-ins.
Okay.
Processes send signals to each other, basically saying, hey, I'm alive.
So like if someone misses a heartbeat, the others know something's wrong.
Exactly. It's the first sign. But just like your group text, there can be false alarms. A network glitch could cause a missed heartbeat, even if the process is fine.
Ah, so how do they avoid jumping to conclusions then?
There are a couple of approaches. Some systems are simple, others more sophisticated, like the SWIM protocol. SWIM actually gets a process's neighbors to check on its health, like a buddy system.
Okay, so less chance of a false alarm.
Yeah, helps reduce those. It makes the system more resilient.
That's clever. But what if a process just stops responding completely? Is there a point where the system says, okay, this is serious, we need to act?
Exactly. That's where timeouts come in. It's like setting a timer when waiting for a friend. Give them time, but if they don't show up, you assume something's up and move on.
Makes sense. So if a process doesn't respond within a set time, it's considered failed. But how do they choose how long to wait? Seems tricky.
It is. Choosing the right timeout is crucial. Too short, you risk those false alarms. Too long, you're slow to react to a real failure. It's a balance, speed versus accuracy.
Right. And the sources mentioned a fire-cruel failure detector. What's that about? Sounds fancier than heartbeats and timeouts.
It is a bit more nuanced. Instead of up or down, it gives you a probability of failure based on recent heartbeat patterns, like a doctor monitoring vital signs. It's not just dead or alive, it's a deeper understanding of the system's health.
So a more detailed picture.
Exactly, much more detailed.
So we've got detecting failures down, but what happens next? If a failure is confirmed, who takes charge to keep things running?
It's a great question. That brings us to leader election. Who gets to call the shots when things get chaotic,
Leadership drama, even in the digital world. So how does this election work? Do they have campaign speeches and promises?
Well, not quite, but there are some interesting approaches.
Right.
One classic algorithm is the bully algorithm.
Bully algorithm. Sounds a bit aggressive.
It does, but it's straightforward. Processes with higher IDs essentially assert themselves as leader, like a group where the most experienced person takes charge in a crisis.
Okay, so seniority wins out.
Yeah, you got it. But there's a potential issue. What if the most senior process is also the least reliable?
Right, that wouldn't be good.
That's why some systems also look at quality metrics. Stability, performance. It's about finding the best fit for the situation.
So not just the title, but the ability to get things done.
Precisely.
Okay, the bully algorithm.
Yeah.
Any other ways they choose leaders?
Absolutely. Another is the ring algorithm. Imagine a token being passed around. Whoever's holding it is the leader.
Like hot potato.
Exactly. Simple but effective. But remember, not all systems are the same. Some have multiple leaders, changing roles depending on the task.
Wow, lots of ways to do leadership here.
It's a diverse world.
It is. Clearly, these systems are adaptable, resilient.
Yeah.
But all this leadership talk makes me think about data consistency. How do they keep those replicated copies in sync when failures happen?
That's a great question. And that takes us to the heart of what makes these systems so complex. We need to talk about consistency models.
Okay, let's do it. I'm ready to go deeper.
All right, let's unpack this concept of consistency models and explore how they keep data in order. Consistency models, think of them like the rule book for how data behaves when you have multiple copies.
Okay, so the rules of the game.
Right. They define what consistent even means when things can go wrong, you know?
Yeah, because communication isn't always instant.
Exactly. And achieving perfect consistency where every read sees the absolute latest right, that can be really hard, really expensive.
So it's like trying to keep a giant orchestra perfectly in sync, beautiful but impossible.
It's a great analogy, and that's why there are different models, different levels of guarantees. It's about balancing consistency with performance.
Okay, so pick the right tool for the job.
Right. So let's look at some examples. One well-known model is linearizability. It basically creates this illusion that all operations happen instantly in one global order.
So everyone sees the same thing at the same time.
Exactly. Like there's only one copy of the data. Linearizability makes it easy to reason about the system, but
it probably comes at a cost, right?
It does. All that coordination, it can slow things down. So not always the best choice if speed is key.
Right. Makes sense. So if that's the gold standard, what are some more relaxed models?
Well, one common one is sequential consistency. It relaxes those strict timing requirements, but still provides some order. All processes see operations in the same order, even if they're interleaved a bit.
So like everyone watching a movie, same order, but maybe arriving at different times.
That's a perfect analogy. And then there's causal consistency.
Oh, yeah, that one was interesting.
It's about preserving cause and effect. Imagine editing a document. If I make a change and you make one based on mine, causal consistency ensures everyone sees them in that order.
Like a chain of events, each action linked to the previous.
Exactly. Now, we can't forget eventual consistency. This one's a bit different.
It's the one that sounds like it'll all work out eventually.
Well, it is a bit more nuanced, but yeah. Basically, if you stop updating data, all the replicas will eventually match. No guarantee they're always in sync, but they'll get there.
Sounds very laid back.
It is, but that's its strength. Availability and performance. It's great for large systems like social media or e-commerce where things are constantly changing.
Yeah, where speed is key. But wouldn't users see different versions of data sometimes?
They might. Managing that is the challenge with eventual consistency. You need to resolve conflicts, handle different versions of truth, make sure it all converges eventually.
So it's a trade-off. Power for complexity.
Precisely. Choosing the right model depends on your needs. Consistency, availability, performance. It's all about finding the right balance.
Well, we've gone from detecting failures to choosing leaders to these consistency models. It's like we've opened up a whole new world.
We have. But just like any complex machine, there's always more to explore.
Okay.
We've talked about the concepts, but how are they actually implemented? How do distributed databases actually stay running smoothly?
That's a great question. I'm ready to go even deeper.
All right, let's dive into anti-entropy mechanisms, gossip protocols, and distributed transactions. Those are the nuts and bolts that make it all work.
All right, so we've covered detecting failures, choosing leaders, and even those consistency models. But how do they all work together? Those sources you shared mentioned anti-entropy and gossip protocols. Sounds a bit mysterious.
It does, doesn't it? But they're key for keeping those data copies in sync, maintaining consistency.
Right.
Let's start with anti-entropy. It's all about actively finding and fixing inconsistencies.
So like a cleanup crew for the database.
Exactly. One way is read repair. When a client reads from multiple replicas and spots inconsistencies, they fix them right there, like catching a typo as you read.
That's efficient, so you're not waiting for problems to build up.
Right. And there's also digest reads.
Oh, what's that?
Replicas exchange summaries of their data, like comparing notes. If they don't match, they investigate to find the exact mismatch and fix it.
Okay, so read, repair, and digest reads. 2 ways to fight inconsistency.
That's right. Then there are gossip protocols.
That one sounds like, well, gossip.
It's not far off. It's about spreading information in a decentralized way. Nodes randomly share updates with each other, like a game of telephone, until everyone gets the message.
So no central authority, they figure it out themselves.
Exactly. Very resilient, especially in large systems. Even if some nodes are down, information still flows.
Clever. But what about when we need to actually change the data? How do they handle updates in a coordinated way?
That's where distributed transactions come in. It's about making sure a set of operations, even across multiple nodes, happens as one unit.
Okay.
Either all succeed or none do. That way, you maintain consistency.
Right, like classic transactions, but more complex with multiple computers.
Exactly. One approach is the two-phase commit protocol 2PC. A coordinator node makes sure everyone is ready to commit before any changes are permanent.
So everyone has to be in sync before the final step.
Precisely. Prevents partial updates, keeps the data consistent.
Makes sense. The sources also mentioned Calvin and Spanner. Are those different ways to handle transactions?
They are. Calvin preorders transactions using timestamps for efficiency. Spanner uses a global clock for consistent ordering across the whole system.
Wow, so many different ways to keep these systems in check. It's amazing how much goes into making them work.
It is. It really shows human ingenuity at its best. We've come a long way in understanding these systems, but the journey continues.
Absolutely. This deep dive has been incredible, revealing the inner workings of those massive distributed databases. I'm seeing those blinking server lights in a whole new light.
I like that. And it's that understanding that lets us build even better systems in the future.
Well said. This deep dive has been fantastic. Thank you so much for sharing your expertise.
My pleasure. And to our listeners, we hope you found this exploration as fascinating as we did.
Don't forget to like, share, and subscribe to The Deep Dive for more explorations like this. Until next time. All right, ready to dive into consistency models? We're talking distributed databases this time.
Yeah, consistency. It's essential but gets more complex when you've got data spread across multiple servers.
Definitely not your simple relational database anymore.
Right. We need to make sure all those copies of data agree on what's the latest version. And that's where consistency models step in. They set the rules.
So guidelines to make sure everyone's on the same page, even though the data is all over the place. Okay, so let's start with eventual consistency, one that pops up a lot. How's that work?
Eventual consistency is about prioritizing availability. You allow for temporary inconsistencies, but the key is they'll eventually converge to the same state. Think of a banking system. You're checking your balance online.
Behind the scenes, multiple servers doing their thing.
Exactly. And even if one server's down for a bit, you can still see your info while the system catches up.
So we're not putting everything on hold just for perfect sync every second.
No.
But how does this fit with that whole consistency, availability, and partition tolerance triangle?
That's where the CAP theorem comes in. It says, in a distributed system, you can only guarantee 2 out of those 3. So with eventual consistency, you're choosing availability and partition tolerance over strict consistency.
Meaning, we got to make choices based on what we need most.
Precisely. There's no one-size-fits-all. Want consistency and partition tolerance, might have to give up some availability. Need high availability A&D partition tolerance. Might mean loosening those consistency guarantees, like we do with eventual consistency.
So finding the right balance, right?
Yeah.
Depends on what the app needs. Okay, now let's look at the opposite end. Strict consistency. How does that even work when we're distributed?
Strict consistency is like having one single source of truth. Every read reflects the most recent write, doesn't matter who's asking, like a single database server. But when you've got data replicated on multiple servers, woof, that's a challenge. You need mechanisms to ensure every update is reflected instantly on all the copies.
So ideal, but probably hurts performance a lot in a distributed world. Which leads us to another one. Linearizability. How's this different?
Linearizability is all about order. It makes sure all operations look like they happened instantly, in a specific order, even if they're on different servers, like there's a global timekeeper making sure everything's in sync.
So imagine people in different countries all booking tickets for a concert.
Exactly. No matter where they are, they see the same ticket availability, and the bookings are processed in a global order. Prevents overbooking, keeps things fair.
Sounds vital when the order of things is super important. But I bet it comes with some overhead.
You're right, it does add complexity compared to something like eventual consistency. More communication between servers to keep everyone up to date. But you get strong guarees about order and visibility, which can be essential depending on what you're building.
Again, trade-offs. Got to choose the right tool for the job. We've got a few more consistency models to look at, though, right? What about sequential consistency?
Sequential consistency is kind of interesting. It relaxes that real-time ordering requirement we see in linearizability, but it still guarantees everyone sees operations in the same order. Imagine folks editing a document together.
Multiple people making changes at the same time.
Right, and with sequential consistency, everyone sees those changes applied in a consistent order, even if it's not in real time. Maybe one user's edits look like they came before another's, even if they were actually made concurrently. The point is, everyone sees the same history of edits.
So it's like synchronized teamwork, but without needing to be perfectly in sync at every second.
Exactly. It strikes a balance between that strict ordering and the flexibility of weaker models. And that flexibility is great when you don't absolutely need real-time order.
All right, so far we've covered eventual consistency, strict consistency, linearizability, and sequential. What about causal consistency? Where does that fit in?
Causal consistency is all about cause and effect. Let's say you update a user profile, and then based on that update, you send a notification.
So two different actions.
Yeah. And causal consistency makes sure that even if they're handled on different servers, the notification is always sent after the profile update is done. Keeps that logical order of events.
Like making sure the story's told in the right order, no matter where you start reading. Seems important for apps with complicated workflows, or those driven by events.
You got it. It helps avoid those weird inconsistencies you can get from concurrent actions in a distributed system, especially when those actions depend on each other.
Wow, this whole consistency model thing is way more nuanced than I thought. Keeping data in sync across multiple servers is a whole other ballgame.
It definitely adds layers of complexity. But understanding these concepts and the trade-offs, that's how you make smart decisions about your distributed database architecture. And honestly, we've just scratched the surface. There's a whole world of techniques and implementations out there to explore.
Right, we'll get to those next time. And for everyone listening, don't forget to like, share, and subscribe to The Deep Dive. For more, we'll see you soon. Back again for more on consistency models. We've talked about the models themselves, but let's get into how they actually work in practice. Like, we mentioned replication keeping multiple copies of data, but how do we make sure they all stay consistent when updates are flying around?
It's a bit like, imagine trying to keep multiple mirrors all showing the same image, but the thing you're reflecting is constantly changing. One way we do this is with anti-entropy. Heard of that?
Rings a bell. Refresh my memory.
Sure. Anti-entropy is a process where replicas, those data copies, they periodically check in with each other. It's to spot and fix any inconsistencies. Like, think of a team working on a document. Everyone's got their own copy.
And every so often they compare notes to make sure everyone's got the latest, right?
Exactly. They catch those little discrepancies before they become big problems.
Yeah, exactly. But do they have to send the whole data set every time? That seems inefficient.
You're right. That would be a nightmare, especially with tons of data. So instead of sending the whole thing, they exchange summaries, like comparing fingerprints instead of the whole person.
So a quick check to see if they match.
Exactly. If the summaries match, we're good. Data's consistent. But if they're different, then the replicas get more specific, send more detailed info to figure out exactly where the differences are and fix them.
Smart. It's like just comparing notes to find the points of disagreement.
Okay,
so we've got anti-entropy. Any other ways to keep those replicas in sync?
Of course. There's read repair. This one kicks in when a read operation, someone trying to access data, hits an inconsistency. Say you're reading data, but the system realizes it's outdated. Read repair will jump in, update that outdated copy before it gives you the data.
So it's fixing things on the fly as it goes. That's pretty slick.
It is. Keeps things consistent without the user even knowing there was a problem. We've also got gossip protocols. Bit different.
Gossip protocols. Now that sounds interesting.
Yeah, with gossip protocols, the replicas share updates randomly with each other. Think of it like, spreading news or rumors in a social network.
I get it. Each replica tells a few neighbors, and then those neighbors tell their neighbors, and so on.
Right. Eventually, all the updates spread through the system, and all the replicas end up consistent.
Decentralized information sharing. Sounds super scalable, especially for massive systems where it'd be a pain to have everyone talk to everyone else directly.
You nailed it. Gossip protocols are known for their scalability, and they're good at handling failures. Even if some replicas are down for a bit, the information can still flow through the network.
So we've got anti-entropy, read repair, and gossip protocols. all different ways to keep replicas in sync. But how do you actually pick which one to use?
Picking the right one depends on the situation, Things like how much consistency you need, how often the data changes, how much bandwidth you have, and how much latency you can tolerate. They all matter.
Another balancing act. Makes sense. Okay, got to circle back to those CRDTs you mentioned before, those self-sorting, conflict-free data structures. How on earth do they work?
CRDTs are a fun one. They use some clever math to make sure updates can be applied in any order without causing conflicts. One key thing they use is commutative operations. Like, think about adding numbers.
2 plus 3 is the same as 3 plus 2.
Right. It doesn't matter which order you add them, the answer's the same. CRDTs are designed with similar ideas, using operations where the order doesn't affect the outcome.
So they're built to avoid conflicts from the very beginning. That's clever.
It is, right. And there are different types of CRDTs, like counters, sets, maps, each with its own rules to handle updates and keep things consistent. Imagine you're tracking likes on a social media post. You could use a distributed counter for that.
So each replica can count likes independently.
Exactly. And even if they're offline, when they reconnect, they can merge their counts using a special function. And this function guarantees the final count is right no matter what order the likes came in.
So it's like having multiple counters that somehow magically combine into one accurate total.
Pretty much. It's how you achieve strong, eventual consistency. Even with all the craziness of concurrent updates and network hiccups, the replicas eventually agree, like a self-healing system.
This is blowing my mind. So we've got consistency models. We've got all these techniques to keep them working. How does someone building a system actually decide what to use? Seems overwhelming.
Yeah, it's not easy. There's no best model or technique. It's about finding the right fit. You need to know what your application really needs, what kind of data you're dealing with, how much consistency is a must-have, how much delay you can handle, and how complex the whole system is.
A lot to think about.
Yeah.
There's no easy answer, is there?
Nope. You gotta weigh the trade-offs and pick the approach that aligns best with your goals. Sometimes you might even use different consistency models for different parts of the same application. It all depends.
So it's not just picking a model and sticking with it. It's more nuanced than that.
Absolutely. It's about finding the sweet spot for your specific needs. Now, let's take a minute to think about everything we've covered so far. Then, in the next part, we'll look at how these choices play out in the real world. For everyone listening, if you're enjoying this deep dive, don't forget to like, share, and subscribe for more insightful explorations. See you soon.
And we're back. Been talking all about consistency models, how they work, the trade-offs. Now let's see how these choices actually play out in the real world.
Yeah, because it's one thing to talk theory, but it's another to see it in action, right? Like, we've gone from eventual consistency to CRDTs. It's clear that picking the right approach can really make or break things.
So any real-world examples where these decisions have a big impact? What comes to mind?
E-commerce is a big one. Think about a hot item on sale. Tons of people trying to buy it at the same time.
Oh yeah, that's got to be a challenge.
If the system's using eventual consistency, some users might think the item's available, even if it's actually sold out.
Oof. Recipe for disaster. Angry customers, logistical headaches, not good.
Exactly. In that situation, you'd really want something stronger, like linearizability. Make sure every transaction is processed in order, globally. No overselling, everyone gets a fair shot.
Right, so it's not just about keeping the data in sync, it's about making sure the whole system works properly. But then what about something like a social media platform? Millions of users posting and commenting all the time.
Good point. Their eventual consistency might actually be fine. A little delay in seeing the latest posts or comments, probably not a big deal for most users.
And keeping things running smoothly is super important when you've got that much traffic.
Exactly. So you prioritize availability over having everything perfectly synced up every millisecond. It's a trade-off, like we've been saying.
Accuracy versus responsiveness. Got it. Any other areas where these choices are really critical?
Finance. When you're dealing with money, accuracy and consistency are non-negotiable. Think about banking. People making deposits, withdrawals.
Yeah, even a tiny error there could be a huge problem.
Right. Incorrect balances, disputes, loss of trust. So in those cases, strong consistency models like serializability or linearizability are essential. Going with a weaker model could be catastrophic.
Really drives home the point that choosing the wrong model isn't just a technical issue. It has real consequences.
Right.
It's about people's money, their trust in the system.
Absolutely. And as we rely more and more on distributed systems and they get more complex, these things become even more important. Developers, DBAs, everyone's got to be aware of these trade-offs to make sure their applications are reliable, scalable, and most importantly, trustworthy.
Well said. This deep dive into consistency models has been eye-opening, to say the least. We've gone from the basics to real-world implications, covered a ton of ground. What's the one big takeaway you want our listeners to remember?
It's this. Consistency isn't just one thing. It's a whole spectrum, a range of possibilities. Each one has its pros and cons. The key is to understand that spectrum and choose the approach that balances consistency, availability, and performance in a way that works for your application.
Couldn't have said it better myself. It's about informed choices, understanding the nuances, and staying adaptable as technology keeps changing. And to everyone listening, if you found this deep dive valuable, don't forget to like, share, and subscribe to the deep dive for more insightful explorations. Until next time.
Okay, ready to dive in. Today we're looking at distributed systems, and how they keep your data straight. It's like, imagine a database, but it's spread across a bunch of servers.
Right. And how do you make sure everything's consistent, even when, things go wrong?
Yeah, exactly, because things always go wrong.
Oh, absolutely. That's a challenge every large-scale system faces. I mean, think about it. Those apps and websites everyone uses, they need to be up all the time.
24/7.
Exactly, even if a server kicks the bucket.
Yeah.
So to pull that off, they use these techniques like anti-entropy and gossip protocols.
Anti-entropy. That sounds kind of intense.
Well, maybe not super dramatic, but it's definitely essential. Basically, anti-entropy is all about spotting those inconsistencies in the data, across all those different servers.
It's like constantly making sure everyone's on the same page.
Yeah, exactly, like a continuous reconciliation. Now, there are a few ways to do this. Each one has its pros and cons, For example, there's read repair. It fixes inconsistencies as they pop up during a read operation.
So say you're checking a price on, Flipkart or Amazon, and the system sees a mismatch, between what's displayed and the actual price in the database. Read repair swoops in and fixes it.
Boom. Just like that. And you wouldn't even notice.
Nice. Okay, so what about digest reads? I've heard that term thrown around.
Digest reads. Now, this is all about efficiency. So instead of comparing these huge data sets, which can take forever and tons of resources, right? Digest reads use hash functions. Think of it as creating a unique fingerprint for each data set.
Okay, so if the fingerprints match, you're good to go. No need to check every detail.
Exactly. Saves a ton of time and effort.
Smart. So then what happens if a server goes offline? Like power outage, network issue, anything like that?
Good question. That's where hinted handoff comes in. Think of it like this. You have this important update, but your friend's phone's off. You're not going to just, toss the update. You'll find a way to deliver it later.
Right, you'd leave a message or something.
Exactly. So in hinted handoff, the update gets stored somewhere else temporarily. And then when that server is back online, boom, the update gets delivered. So even with these temporary disruptions, nothing gets lost.
So we've covered these mechanisms for catching inconsistencies during reads. What about when updates need to be made across all the servers?
Great point. And that's where things get even more interesting. So to handle these updates, especially with massive data sets, you often use something called a Merkle tree.
A Merkle tree? What is that, some kind of magical tree?
It kind of sounds like that, right? But it's really powerful. Picture it like a hierarchical data structure, like a family tree but upside down. The roots at the top, and each branch represents a part of the data. The leaves are the individual data blocks.
Okay, I'm following so far.
Now, the cool part is how this tree is built. Each node has this thing called a cryptographic hash, like a digital fingerprint of all its children.
So if you change even a tiny bit of data in one of those leaves, it changes everything all the way up to the root.
Bingo! And because of this, you can quickly compare two Merkle trees. It's super efficient for finding those differences, like having a map that highlights only the streets that have changed in a city rather than checking the whole city.
Wow, that's pretty efficient. I can see how that would be super useful. So how do updates actually spread through the system? How does everyone get the memo?
Well, that's where these gossip protocols come in. Think about how, friends share news and updates. They chat, information spreads organically.
Like word of mouth, but for servers.
Exactly. And in a distributed system, each node is like a friend, constantly sharing info about the data and the system's health.
Okay, but doesn't that lead to a ton of messages flooding the network? Wouldn't that be super inefficient?
Yeah, you got to be smart about it. Gossip protocols have ways to minimize that redundancy. They make sure messages are only sent when they need to be. For example, using timestamps so they know what's already been shared.
So it's like targeted gossiping.
Exactly. And the other cool thing is they can actually help detect failures. Remember how nodes are always chatting? If one goes silent, its neighbors notice pretty quickly.
Like if someone's missing from their usual chai spot, you'd wonder what happened.
Exactly. That missing node could mean trouble. And because this spreads through the gossip network, the system can isolate that failed node. Prevents bigger problems.
It's like a built-in alarm system. Okay, so how does this failure detection actually work? Is there a special process for it?
There are these things called failure detectors, algorithms running on each node, always analyzing those gossip messages.
So they're basically trying to figure out if the other nodes are alive and well.
Yep. They look at things like, how often messages are sent, the information in them, how long it's been since the last one.
Like a detective piecing together clues. But wouldn't it be bad if they were too quick to say a node failed? Or if they waited too long?
Oh, absolutely. It's a balancing act. You don't want false alarms, but you don't want to miss real problems either.
Got it. So finding that sweet spot is key. Man, this is complicated stuff. Who knew so much went on behind the scenes?
Right. And we've only scratched the surface. There's a whole lot more to uncover.
Well, I'm ready to keep digging. But maybe let's take a quick pause here. Let everyone digest what we've covered.
Good idea. A little mental break never hurts. We'll be back soon to wrap things up and maybe leave you with something to think about.
All right, welcome back. So let's unpack these gossip protocols. They sound, almost too casual for something this important.
I know, right? But they're super powerful. Remember we talked about friends sharing news? Well, in a distributed system, the nodes, they're like those friends. They're constantly swapping information about the data and how the system's doing.
So it's not like a central authority calling all the shots. It's more like everyone's keeping each other updated.
Yeah, exactly. And it's happening all the time across the whole network. So it's really efficient and resilient, Even if a few nodes are down where the network's acting up, that information will get through.
Okay, that makes sense. But doesn't that mean there are tons of messages flying around? Wouldn't that be, super inefficient?
That's a good point. But gossip protocols are designed to be smart about it. There are ways to cut down on all those extra messages. They might use timestamps to track what's already been shared.
Oh, so they're not just blindly gossiping. More like sharing information strategically.
Exactly. And here's the other cool thing. Gossip protocols can help spot failures. Remember how we said the nodes are always talking? Well, if one goes quiet, the others notice right away.
Like, hey, where'd they go?
Yeah. And that missing node, well, it could mean something's wrong. And because that information gets spread through the gossip network, the system can react quickly, isolate that failed node before things get worse.
It's like a built-in safety net. So how does that actually work? The failure detection part, I mean.
So there are these things called failure detectors. They're like algorithms that run on each node. And they're constantly checking those gossip messages.
Trying to figure out if everyone's still up and running.
Exactly. They look at stuff like how often messages are sent, what's in those messages, how long it's been since the last one, all that.
So it's like a detective gathering clues and trying to solve the mystery?
Pretty much. But, wouldn't it be bad if they were too quick to declare a node as failed? Or if they waited too long?
Yeah, that could cause problems.
It's all about balance, right? You don't want false alarms, but you don't want to miss real issues either.
Finding that sweet spot is key. Man, distributed systems are complicated. There's so much going on behind the scenes.
I know, right? And we've just scratched the surface. There's a whole lot more to explore.
I'm ready to keep learning, but maybe let's give everyone a minute to process all this. We've covered anti-entropy, gossip protocols, Merkle trees, failure detectors. It's a lot.
A good point. A little break is always good. We'll be back soon to wrap up and maybe leave you with some food for thought.
Okay, so we've talked about all these mechanisms, but what about transactions? Those operations that have to happen across multiple servers. How do you make sure everything happens correctly even if something goes wrong?
Transactions. That's a tough one, One of the trickiest things to get right in distributed systems, imagine transferring money between bank accounts, but those accounts are on different servers.
Right, you can't have half a transaction. Either both accounts get updated or neither.
Exactly. And that's where distributed transactions come in. They make sure that a bunch of operations, even if they're spread across different nodes, are treated as one single unit. It's all or nothing.
Makes sense. But how do you actually pull that off, especially when things can fail independently?
Well, one common way is two-phase commit, or 2PC. Think of it like an orchestra, right? Before they start playing, the conductor checks with each musician. Are you ready?
So it's like a readiness check before the big performance.
Exactly. In 2PC, there's a coordinator node, kind of like that conductor. It sends a prepare message to all the nodes involved in the transaction, and each node checks if it can do its part.
So everything looks good, they give the green light?
Yep. A yes vote. But if something's wrong, like a server's running out of space, they send a no vote.
So everyone has to be on board for the transaction to go through.
Now, if the coordinator gets yes votes from everyone, it's go time. It sends a commit message. Everyone finalizes their part of the transaction.
Like the conductor giving the downbeat and the music starts.
Perfect analogy. But what if, like, a musician misses the cue? Or a server crashes?
Yeah, that wouldn't be good.
Things get messy, and 2PC has its limits. Like, if a node fails before voting, the coordinator can just abort the transaction, no harm done. But if it fails after saying yes but before the commit,
Oh.
that's a problem. It's in this uncertain state. We don't know if the transaction happened or not.
Sounds like that could lead to inconsistencies.
Yeah, it's a classic issue. But there are more advanced protocols like three-phase commit or Paxos. They're more complex, but they handle failures better.
So it's always a trade-off. Complexity for robustness. It seems like reaching agreement in a distributed system is way harder than in, say, a single database.
You got it. In a single database, there's one boss, one source of truth. But in a distributed system, getting everyone to agree, especially when things are failing left and right, that's a whole different ballgame.
So that's why those consensus algorithms you mentioned earlier are so important, right?
Bingo! They make sure all the nodes eventually agree. They're like the foundation for building those reliable systems we rely on.
Wow. This has been quite the deep dive. We've gone from anti-entropy and gossip protocols to, like, the nitty-gritty of transactions and consensus. It's amazing how much is happening behind the scenes of all those apps and services we use every day.
It really is. And honestly, we've barely scratched the surface. This field is constantly evolving. There's always something new to learn.
Well, I think it's time to wrap things up for today. But if you enjoyed this deep dive, be sure to like, share, and subscribe to our channel. And keep those questions coming. We love exploring this stuff with you.
Absolutely. See you next time.
Okay, so today we're going to be looking at distributed transactions.
Right.
And, obviously everyone listening knows how important transactions are
Yes.
in relational databases, to keep everything consistent when multiple things are going on at the same time.
Right.
But when we get to systems where the data lives on multiple servers,
Yes.
then things get a lot more complex.
Yeah. It's a whole new ball game. Imagine trying to coordinate changes across a network of servers.
Yeah.
And, each one has its own piece of the data.
Right.
And you have to account for servers, crashing network failures and just make sure that every server agrees on the outcome.
Oh, it's like a nightmare.
It can be.
So how do these distributed systems make sure that the data
Right.
doesn't end up just like a jumbled mess?
Well, the foundation is something called atomic commitment.
Okay.
And it's a core concept in distributed transactions.
Yeah.
That ensures that all of the participating nodes in a transaction either commit the transaction or abort the transaction together.
Gotcha.
So it's all or nothing. And that's essential for maintaining data integrity.
So there's no room for like one server going rogue and committing when others are left behind.
Exactly right. So if one part of the transaction fails, the entire transaction is rolled back across all the servers.
Okay.
And that prevents inconsistencies.
Yeah.
And to manage all of this, we often have a designated coordinator node that orchestrates the whole process.
Interesting. Can you give me an example of a specific approach?
The classic method is the two-phase commit protocol, or 2PC.
Okay.
And in the first phase, the coordinator checks if all the participating servers, which are called cohorts, are ready to commit the transaction.
So it's like a roll call.
Right. It's like a roll call to see if everybody's on board.
What happens in the second phase?
So in the second phase,
Well,
based on the responses from the first phase,
okay.
the coordinator instructs all the cohorts to either commit or abort.
Right.
And if even one cohort disagrees or doesn't respond, the entire transaction is aborted.
So that seems pretty straightforward.
Yeah.
Are there any downsides to this approach?
But 2PC is widely used.
Yeah.
But it does have limitations.
Okay.
A major one is its vulnerability to coordinator failures.
Oh.
So if the coordinator crashes at a critical moment during the process, the cohorts can get stuck.
Right.
They don't know whether to commit or abort.
Right.
And that can lead to data inconsistency.
That sounds risky. Are there alternatives to address this issue?
Yes. One alternative is the three-phase commit protocol, or 3PC.
Right.
And it introduces an extra phase to try and make the process more resilient to coordinator failures. However, this added resilience comes at the cost of increased complexity and potential performance overhead.
So it's like a trade-off
Right.
between robustness and efficiency.
Exactly.
Now, earlier you mentioned some other approaches that sound interesting.
Yes.
Like Calvin Spanner and Percolator. What makes them unique?
So all of these offer innovative ways to handle these distributed transactions. Calvin, for example, predetermines the order of all the transactions. And that can significantly improve performance. It uses what's called a sequencer to assign a global order to transactions. And then it uses schedulers and workers to execute those transactions on specific servers. And by knowing the order of the transactions in advance, it can avoid a lot of the locking and communication overhead that you would see with two-phase commit.
That's pretty clever.
Yeah.
So what about Spanner? What makes that one stand out?
So Spanner is Google's globally distributed database. And it's known for its strong consistency. And it achieves this by using a globally synchronized clock called TrueTime. And this clock allows Spanner to determine the precise order of transactions, even if they occur across geographically distant servers.
So even if transactions are happening in different parts of the world,
that's right.
Spanner can keep them in sync.
Yeah, that synchronized clock helps maintain data consistency across its vast distributed infrastructure.
Now, Percolator, another system developed by Google, uses a different approach called snapshot isolation.
That's right.
So does that mean that each transaction kind of operates on its own specific snapshot of the database?
So by providing each transaction with its own consistent snapshot, it reduces the need for locking, which can improve performance and concurrency.
Interesting. So how does Percolator handle situations where like multiple transactions want to modify the same data?
It uses a first committer wins rule to manage write conflicts.
So it's like a race to the finish line for those transactions. So these various approaches are fascinating. We have 2PC and 3PC, which prioritize consistency, even at the risk of temporary unavailability. Then we have Calvin, which predetermines transaction order for efficiency. And then Spanner, which uses this global clock for strong consistency across vast distances. And then Percolator, which aims for performance improvements through snapshot isolation. It's incredible to see how all these different approaches address these challenges.
It really highlights the ingenuity and creativity within the field of distributed systems.
I'm definitely feeling overwhelmed with information, but also incredibly intrigued. What are some key takeaways you think our listeners should remember from this initial dive?
I think the key takeaway is just understanding that distributed transactions are complex.
But they're absolutely crucial for maintaining data consistency in modern distributed applications. And there's no one-size-fits-all solution. The best approach depends heavily on the specific needs of the application.
Gotcha. So it seems like there's always a trade-off to consider.
You've hit on a fundamental concept in distributed systems called the CAP theorem. And it states that in any distributed system, you can only guarantee two out of three properties. Consistency, availability, and partition tolerance.
Wait, only two?
Only two.
So you're saying it's impossible to have a system that's consistent, always available, and can handle network partitions.
That's exactly what the CAP theorem posits. And it really highlights the inherent limitations that we face when we're designing these systems. We have to make choices based on the specific needs of our application.
So we've talked about consistency.
We've touched upon network partitions.
But
could you elaborate on what availability means in this context?
Availability essentially means that the system remains responsive to requests. Even if some components of the system fail. So imagine like a shopping website during a huge sale. If one server goes down, the site should ideally keep functioning, maybe with slightly slower response times rather than crashing entirely.
So even if some parts of the system are down, availability ensures that users can still interact with it.
That's the goal.
So if I understand this correctly,
yes,
the CIP theorem means that when a network partition happens,
Right.
You had to choose between either consistency
Yes.
or availability.
That's the trade-off. You
Yeah.
can prioritize having consistent data
Okay.
across all the servers,
Right.
but potentially make some parts of the system temporarily unavailable,
Okay.
or you can ensure that the system stays responsive, even if it means serving data that's slightly stale or out of date.
Okay.
And the choice really depends
Right.
on what the needs of the application are.
Choosing between those two sounds like a tough call,
It can be a tough call.
especially when different applications have different priorities.
Absolutely.
Can you give some real-world examples of how this plays out?
Certainly.
I
So
think
let's consider a banking system.
Okay.
In a banking system, consistency is paramount.
Right.
Imagine transferring money from one account to another.
Right.
The system absolutely has to make sure
Yeah.
that the money is deducted from the source account
Right.
and added to the destination account consistently.
Right.
Even a slight inconsistency could have disastrous consequences.
You definitely don't want to end up with money magically appearing
Right.
or disappearing.
Exactly. So in a banking system,
Yeah.
you might accept brief periods of unavailability
Okay.
to guarantee that absolute consistency.
So in that situation, you would rather have the system be unavailable for a short time
Exactly.
to make sure that the data is consistent.
Yes, because you don't want inconsistencies
Right.
when it
That-
comes to people's money.
Absolutely.
Yeah.
Now contrast that with something like a social media platform.
Okay, good example.
In this case, availability might be more important.
It probably is, because users expect
Right.
to be able to post and view content,
Right.
even if there are temporary network glitches.
Yeah.
So here, it might be acceptable
Okay.
to have slight inconsistencies,
Okay.
such as a delayed update
Right.
in the number of likes on a post,
Right.
in order to maintain that seamless user experience.
So in that case, you're prioritizing that the users can constantly be interacting
Yes.
with the platform,
Yes.
even if there are minor inconsistencies that can maybe be reconciled later.
That's right. It's all about understanding the trade-offs
Wow.
and choosing the best approach for the specific situation.
This CAP-P theorem is really helpful
Is.
for thinking about these choices.
It provides a nice framework.
Now, bringing it back to our discussion of distributed transactions, how do these different atomic commitment algorithms
Right.
align with this framework?
So most atomic commitment algorithms, like
Okay.
two-phase commit and the three-phase commit,
Right.
typically lean towards what we would call the CP side of the spectrum.
Okay.
So they prioritize consistency and partition tolerance.
Okay.
They guarantee that all servers agree on the outcome of the transaction, even if there's a network split, but they might become temporarily unavailable
Okay.
during that partition.
So they emphasize consistency,
Yes.
even if it means sacrificing availability for a
That's
short period.
That's right. Now, Calvin, with its predetermined transaction ordering,
Yeah.
also generally falls under that CP category.
So both 2PC, 3PC, and Calvin
Right.
prioritize consistency.
Yes.
What about Spanner
Right.
with its globally synchronized clock?
Yes.
It seems like it would be even more stringent about consistency.
Spanner definitely aims for strong consistency. But it's important to note
Yeah.
that even Spanner isn't immune to the limitations of the CAP theorem
Okay.
in the face of really severe network issues.
Right.
Even Spanner might have to make a choice.
Right.
But its design is such that
Yeah.
it really strives to minimize those scenarios.
Yeah. So it seems like achieving perfect consistency
Right.
in a distributed system
Yeah.
often comes with trade-offs,
It often does.
at least under certain conditions.
Right. And it's not always just about choosing between consistency and availability.
Okay.
We also have what we would call the AP side of the spectrum,
Okay.
where systems prioritize availability and partition tolerance.
So these AP systems
Yes.
are those that choose to stay responsive,
Yes,
even if it means temporarily compromising on consistency.
exactly. And these systems are designed to handle scenarios
Okay.
where, network connectivity is unreliable
Right.
and they favor responding to your requests,
Right.
even if it leads to temporary inconsistencies, which are
Okay.
then reconciled later on.
It sounds like managing those inconsistencies could become really complex.
It does introduce complexity.
Yeah.
And handling and reconciling those data divergences
Yeah.
is a key challenge for these AP systems.
Right.
But they offer advantages
Yeah.
in terms of flexibility
Okay.
and tolerance to that network instability.
So it's not just consistency versus availability.
Right.
We also have performance to consider.
Absolutely. Performance plays a crucial role.
Yeah. How does that factor into our choice
Right. So, for example,
of distributed transaction approach.
while two-phase commit guarantees consistency,
Right.
it can be slow due to its multi-phase communication process.
Right.
So if speed is a primary concern,
Yeah.
alternatives like Calvin with its predetermined order
Right.
or Percolator with its snapshot isolation might be more suitable.
So we're constantly juggling these three things.
It's a constant balancing act.
Consistency, availability, and performance.
Yeah.
Trying to find the right balance for our specific application.
Exactly. And the CAP theorem really helps us understand those trade-offs and guides us toward making those informed design choices.
Earlier, we talked about this concept of distribution transparency.
Yes.
Hiding the complexities of the distributed system from the user.
Right.
But with all of these intricate mechanisms and trade-offs,
Right.
is it truly possible to create that seamless experience
That's a question.
for the user?
That keeps a lot of database researchers and engineers up at night.
Yeah.
While we strive for seamlessness, there will always be limitations in any distributed system.
Right.
The key is to try to make those limitations as transparent
Right.
and as manageable as possible for the user.
So we aim to create this illusion of a single,
Yes.
unified system,
Right?
while acknowledging the reality
Yes.
of network partitions, consistency challenges, and performance trade-offs.
That's right. That's the ongoing quest
Yeah.
in distributed systems to make the complex feel simple.
Speaking of complexities,
Yeah.
we talked about atomic commitment,
Right.
ensuring agreement on transaction outcomes.
Yes.
But what happens if a server crashes
Right.
in the middle of a transaction?
That's a great question.
How do we ensure fault tolerance in those situations?
So fault tolerance is crucial.
Right.
We need mechanisms to handle those server failures
Yeah.
and ensure that transactions can still complete successfully.
Right.
This is where techniques like replication and logging come in.
Okay, so replication, I'm assuming, means having multiple copies of the data
Yes,
on different servers.
exactly. Replication provides redundancy.
Okay.
So if one server crashes, others with copies of the data
Right.
can continue processing requests.
Right. But then that introduces a whole other challenge
It does.
of keeping those replicas consistent.
You got it. So we're back to the consistency problem again.
That's at square one.
And that's where logging plays a vital role.
Okay.
By recording every operation performed during a transaction.
Okay.
We can reconstruct the system state.
Right.
Even if a server crashes.
It's like having a detailed logbook to trace back the steps
Precisely.
and make sure that nothing is lost.
Logging helps ensure consistency,
Right.
even when we're dealing with failure.
Okay, that makes sense. But what about the log itself?
Right.
How do we ensure that it's durable
That is crucial.
and doesn't get corrupted or lost?
That's a crucial consideration. The log needs to be stored reliably.
Okay.
Usually it's stored on a separate, highly reliable storage system,
Okay.
often with its own replication mechanism for
Right.
added redundancy.
So it's like having a backup of the backup
Exactly.
to make sure that crucial information is protected?
Protecting that log is vital
Right.
for maintaining the integrity of the entire system.
Okay, so we've journeyed through this intricate world of distributed transactions,
Yes.
from atomic commitment to the CAP theorem, replication and logging.
It's a lot to take in.
It's amazing to see how complex these mechanisms are
It is.
that ensure data consistency and fault tolerance.
It really is a testament to the brilliant minds
Yeah.
that have tackled these challenges.
And as we move towards even more distributed systems,
Right.
these mechanisms are going to become even more crucial.
Absolutely.
Now, this deep dive has been incredibly insightful.
It has been.
Any final thoughts for our listener before we wrap up?
Yeah, I think the key takeaway is just to remember that distributed transactions are complex,
Yeah.
but they're essential for modern applications. And
Right.
understanding the core concepts
Right.
and the trade-offs involved
Right.
is key to designing and managing these systems effectively.
Well said. It's about choosing the right tools
Yes.
and approaches to match your needs.
Exactly.
And this deep dive has given our listeners a great foundation to build upon.
I think so.
This has been a fascinating exploration of distributed transactions.
It has been.
Thank you for sharing your expertise with us.
My pleasure.
And to our listeners, if you found this deep dive helpful, be sure to like, share, and subscribe for more insightful explorations into the world of technology. Until next time.
One common technique is called leader-based replication.
Oh, okay.
And in this approach, one of the replicas is designated as the leader.
Right.
And all the write operations are directed to the leader.
Okay.
The leader then propagates those changes to the other replicas, which are called followers.
So it's like a hierarchical structure.
Right.
Where the leader is dictating the changes.
Yes.
And the followers are keeping in sync.
Yeah, it simplifies things.
Okay.
Because there's a single point for managing all the updates.
But what if the leader fails?
Right.
Does the whole system come to a halt?
Not necessarily.
Okay.
Leader-based replication systems are designed to handle leader failures.
Okay.
So if the leader crashes,
Right.
the remaining replicas will elect a new leader from amongst themselves.
Right.
And operations can continue.
So it's like having a backup leader ready to take charge.
Exactly.
But how do the followers make sure that they're applying the changes from the leader in the right order?
Yeah.
Especially if there are network delays or message losses.
That's a good question.
Yeah.
That's where we use techniques to ensure that the order of operations is consistent across all the replicas.
Okay.
One such technique is called write-ahead logging.
Write-ahead logging.
Yes.
Does that mean writing a record of the operation?
Yes.
Before it's actually applied to the data?
That's the idea. So before making any changes,
Okay.
the leader writes a record of the operation to a log.
Okay.
And that log is then replicated to the followers.
Okay.
So this log acts as a source of truth
Right.
for all the replicas.
So even if a follower crashes and restarts,
Yes.
it can replay the log
Exactly.
to catch up with the latest changes.
That's right.
Okay.
Write-ahead logging really helps ensure that consistency, even when you're dealing with failures.
What about the log itself, though?
Right.
How do we ensure that it's durable
Yeah.
and that it doesn't get corrupted or lost?
That's a crucial consideration. The log needs to be stored reliably.
Okay.
Usually it's stored on a separate, highly reliable storage system, often with its own replication mechanism.
Okay, so it's like a backup of the backup.
Exactly.
To make sure that that crucial information is protected.
Yeah. Protecting that log is really vital for maintaining the integrity of the whole system.
We've journeyed through this intricate world of distributed transactions.
We have.
From atomic commitment to the CAP theorem replication and logging.
Yes.
It's really amazing to see how complex these mechanisms are.
It's a testament to the brilliant minds
Yeah.
who have tackled these challenges.
And as we move towards even more distributed systems, these mechanisms are only going to become more crucial.
Absolutely, and more complex.
This deep dive has been incredibly insightful.
It has.
Any final thoughts for our listener before we wrap up?
I would just say that, distributed transactions are complex. Yeah.
But they're essential for modern applications.
Right.
And understanding those core concepts and the trade-offs involved is key to designing and managing these systems well.
Well said. It's about choosing the right tools and approaches to match the specific needs of your application.
Yes.
And I think this deep dive has given our listeners a great foundation to build upon.
Yeah.
This has been a fascinating exploration of distributed transactions.
It has been.
Thank you for sharing your expertise with us.
My pleasure.
And to our listeners, if you found this deep dive helpful, be sure to like, share, and subscribe for more insightful explorations into the world of technology. Until next time.
Okay, so today we're diving deep into consensus algorithms. And I know our listeners are pretty familiar with relational databases and how important it is to have, consistent and reliable data there.
Yeah.
But when you move into the world of distributed systems, things get a little trickier.
Yeah, a lot trickier, yeah.
Especially when data is spread across all these different nodes.
Exactly. Yeah, you've got unreliable networks to worry about.
Right.
You could have nodes crash. You don't have that single clock to keep everything in sync.
Yeah, that makes sense.
It's kind of like if you're trying to get a large family to agree on dinner plans.
Yeah.
There's always going to be like one person who's late or changes their mind.
Yeah, always one.
It's never simple.
So how do we make sure then that all of these nodes in a distributed system agree on the same information?
That's where consensus algorithms come in. They're really the key.
Yeah.
They help to ensure that all of those nodes will eventually reach a consensus, even with those potential disruptions. It's really essential for maintaining that data integrity and also that overall system stability.
So it's like having this referee then who's making sure everyone's playing by the same rule.
Yeah, that's a good way to put it.
But how does that actually work in practice? I mean, it can't be as easy as just like asking everyone to agree, right?
You're right. It's definitely not that simple.
Yeah.
One of the kind of fundamental challenges we have here is captured by a concept called the FLP impossibility result.
The FLP impossibility result.
Yeah.
That sounds a little intimidating.
It is a bit theoretical.
Okay.
But essentially what it says is that in a completely asynchronous system where we don't have any guarantees about how long messages take to be delivered, reaching a consensus in a fixed amount of time, it's impossible if even one node might fail. So imagine trying to, like, schedule that family dinner.
Oh, yeah.
But you have no idea when everyone's going to respond. Or if someone might suddenly not be available.
Yeah, I can definitely relate to that scenario. So does that mean then that we can never truly achieve consensus in a distributed system?
Well, not necessarily. The FLP result kind of highlights those limitations of working in purely theoretical conditions.
Okay.
In reality, we actually make certain assumptions about the system.
Right.
So, for instance, most consensus algorithms operate under the assumption that the majority of the nodes are functioning correctly.
Right.
And that the messages will eventually be delivered.
Okay.
So it's about kind of finding that practical balance between the ideal and the reality of how these systems actually work.
Right. The ideal versus the reality.
Exactly.
Okay, so let's talk about some of the specific algorithms then that have been developed to tackle this challenge.
Okay, sure.
One of the most well-known that I've heard of is Paxos.
Yeah, Paxos is a classic.
Classic.
It's been around for a while.
Right.
And it's designed to work even in systems where messages might be delayed.
Okay.
Or nodes could crash.
Wow.
So it's very robust.
Yeah, so Paxos, it's a reliable workhorse, it sounds like,
Yeah, you could see that.
in the world of consensus algorithms.
Yeah, and it's been widely used in distributed databases.
Okay.
And other systems like Google Spanner, you've probably heard of that,
Yeah.
and Apache Zookeeper as well.
Okay, so can you give us like a simplified explanation of how Paxos actually works?
Sure. Imagine you have a group of people and they're trying to agree on a single value.
Okay.
In Paxos, there are these three key roles.
Right.
You have proposers, acceptors, and learners.
So it's like this mini democracy then trying to reach a decision.
Exactly, yeah.
That's a great way to put it.
So the proposer will suggest a value, the acceptors, they vote on it,
Okay.
and then the learners will observe that outcome.
Got it.
So Paxos ensures that only one value can be chosen, even if multiple proposers are competing.
That makes sense.
Yep.
So how does it handle then the possibility of messages getting lost or nodes failing?
Well, that's where the cleverness of the algorithm really comes in. Okay. It uses a series of message exchanges and timeouts
Okay.
to guarantee that a majority of the acceptors will eventually agree on the same value, even with those uncertainties.
So it's like having a backup plan for every potential hiccup in communication.
You could say that, yeah.
Okay, that's really interesting.
Yeah, and because of that robustness, Paxos has been a cornerstone of many distributed systems.
But you mentioned that Paxos is just one of the algorithms out there.
Yeah, exactly.
Are there others that are commonly used?
Yeah, absolutely. Another popular one is called Raft.
Raft. Okay, tell me more about that one.
So Raft focuses on simplicity
Okay.
and ease of understanding.
Okay.
So instead of having multiple proposers competing, like in Paxos, Raft actually elects a single leader.
Okay.
And that simplifies the process of reaching consensus.
So it's like having like a designated captain to steer the ship
Yeah, exactly.
and make the final call.
The analogy, yeah.
So the leader proposes the values.
Yes.
And then the other nodes, you said they're called followers.
Yeah, the followers, they replicate those values to ensure that everyone stays in sync.
So it's a more streamlined approach to achieving consensus.
Exactly.
Oh,
and that makes it a really popular choice for many applications.
Yeah, that makes sense.
Yeah.
So this is all really fascinating, but what happens if we can't fully trust all the nodes in a system?
Okay.
Like, what if some nodes are intentionally, like, trying to disrupt the process or spread misinformation?
Well, that's where Byzantine consensus comes into play.
Byzantine consensus.
Yeah.
That sounds intense.
Yeah, it is.
Tell me more.
So it's specifically designed to handle those scenarios where some nodes might be malicious or exhibiting arbitrary behavior.
Okay.
And it's actually named after the Byzantine generals problem.
Okay.
Have you heard of that?
I have heard of that.
Yeah.
It's like a thought experiment, right?
Exactly.
Where these generals need to agree on a plan of attack, even if some of them are traitors.
Exactly, yeah.
Wow, that's a very high-stakes situation.
It is.
To need that kind of a system.
Yeah, and so Byzantine consensus algorithms are designed to ensure that the system can still reach agreement,
Okay.
even if a certain number of nodes are acting unreliably or maliciously.
So it's like you have a system that can filter out the noise.
Yeah.
And reach a consensus, even when some participants are trying to sabotage the process.
That's exactly right.
That's incredible.
Yeah, and this type of consensus is actually crucial in applications like blockchain technology,
Right.
where decentralization and trust are paramount.
Okay, so we've got Paxos, we've got Raft, and then we have Byzantine consensus.
Yeah.
All tackling this challenge of reaching agreement in different ways.
Yeah, different approaches.
Okay, are there any other consensus algorithms that we should be aware of?
Yeah, there are many others out there, each with their own strengths and weaknesses.
Okay.
But Paxos, Raft, and Byzantine consensus are definitely some of the most well-known and influential in the field.
It's amazing to me how much complexity there is in this seemingly simple idea of just getting everyone to agree.
Yeah, it seems simple on the surface.
Yeah.
But yeah, there's a lot going on under the hood.
Yeah, it's a very complex process.
It is, and it's a field that's constantly evolving, too.
Oh, really?
Yeah, as researchers are developing new algorithms to kind of address those emerging challenges like scalability and security.
That makes sense.
Yeah.
So we've covered the basics of consensus algorithms and touched upon some of these key players like Paxos, Raft, and Byzantine consensus.
Right.
But I'm curious, how do these algorithms actually play out in real-world scenarios?
Yeah, that's a great question.
Can you give us some concrete examples?
Sure. Let's take the example of a distributed database,
Okay.
like Apache Cassandra.
Cassandra.
Okay. It's a popular choice for a lot of applications.
Yeah, for sure.
So Cassandra uses a gossip protocol,
Okay.
which is a type of consensus algorithm to maintain consistency across its nodes.
Okay.
It's kind of like a network of friends sharing the latest news, making sure that everyone eventually gets the same information, even if some of those connections are unreliable.
So even in something as common as a database,
Right.
consensus algorithms are working behind the scenes
Yeah, they're essential.
to keep everything in sync.
Right, they're kind of the unsung heroes,
Yeah.
ensuring that your data remains consistent,
Okay.
even when nodes join or leave the network,
Right.
or they experience failures.
That makes a lot of sense.
Yeah.
What about other applications? Where else do we see these consensus algorithms?
Another great example is cloud storage services,
Okay.
like Google Drive or Dropbox.
Services that we use every day.
Yeah, exactly. Everyone uses those.
Pretty much.
And these services use consensus algorithms to keep your files synchronized
Okay.
across multiple devices.
Right.
So even if you, let's say, edit a file on your phone, those changes are going to be reflected on your computer and any other devices that you have.
And that's all thanks to consensus algorithms.
Yeah, it's really incredible when you think about it.
It is.
How these complex algorithms are powering such seamless experiences, without us even realizing it.
Yeah, they're kind of like working in the background.
Yeah, they're behind the scenes making everything work smoothly.
Right, exactly.
Yeah.
So it really highlights how fundamental consensus algorithms are to modern computing.
They really are, yeah.
They're kind of the invisible glue holding many distributed systems together.
Exactly.
Now, going back to blockchain for a moment.
Okay.
You mentioned that it relies on Byzantine consensus.
Right.
But I've also heard terms like proof of work and proof of stake.
Yeah, those are important too.
Can you explain how those fit into the picture?
Sure. So proof of work and proof of stake are actually specific consensus mechanisms that are used in blockchain technology.
Got it.
And they're ways of determining which node gets to add the next block to the blockchain.
So they're like the rules of the game for deciding who gets to contribute to the blockchain's history.
That's a good way to put it.
Okay, so proof of work, I remember we talked about this earlier, is the one where miners solve these complex mathematical puzzles.
Yeah, they're computationally intensive.
Right.
So the first miner to actually solve the puzzle gets to add the block.
Okay.
And they're rewarded with cryptocurrency.
So it's a competition.
Yeah.
Where the winner gets the prize.
Yeah, in a way, yes.
Okay.
Now, proof of stake takes a bit of a different approach.
Right.
So instead of relying on that raw computational power, it selects validators.
Okay.
Based on the amount of cryptocurrency they hold.
Okay.
And that they're willing to stake as collateral.
So it's more like a lottery then.
Yeah, you could think of it that way.
Where your chances of winning are proportional to your stake.
Exactly.
Yeah.
That makes sense.
And because these validators have something to lose, they're incentivized to act honestly.
Right, because they don't want to lose what they put up.
Exactly, yeah. Okay, so both proof of work and proof of stake are types of Byzantine consensus mechanisms.
Yes, they are.
Used in blockchain.
Yes, they both aim to achieve consensus in a decentralized environment
Okay.
where not all participants can be fully trusted.
Right, because that's kind of the nature of blockchain, right?
Exactly.
It's decentralized, so you don't necessarily know
They don't know who everyone is.
who you're interacting with.
Right.
Yeah, that's really interesting.
Yeah, but they use different approaches
Okay.
to achieve that goal.
Makes sense.
Yeah.
So this is all incredibly fascinating.
It is a really interesting area.
I'm starting to see just how pervasive consensus algorithms are in the technologies that we use every day.
They really are everywhere.
Now, let's shift our focus back to Byzantine consensus for a moment.
Okay.
We talked about it in kind of a general sense.
Right.
Can we dive a bit deeper into how it manages to achieve agreement, even with those potentially malicious nodes?
Absolutely. So Byzantine consensus, it's all about achieving agreement. Even when you have nodes that might be intentionally lying or behaving erratically.
Okay.
So again, imagine those generals who are trying to coordinate an attack.
Right.
But some of them might be traitors sending false information.
Right.
Or trying to sabotage the plan.
Yeah, which is, a recipe for disaster.
Yeah, it would be without Byzantine consensus.
Right.
These algorithms are actually designed to handle these exact scenarios.
Okay.
One of the key ideas is redundancy.
Okay.
So Byzantine consensus typically requires a higher number of nodes to participate
Okay.
compared to algorithms that assume all the participants are honest.
Right. So it's like having multiple sources of information then to cross-check and verify.
That's a good way to think about it.
Okay.
Another crucial aspect is using cryptographic techniques
Okay.
to sign and verify messages.
Okay.
And this helps to ensure that the messages haven't been tampered with
Okay.
and that they actually came from the sender that they claim to have come from.
So it's about creating this system where it's extremely difficult for these malicious nodes to deceive the honest ones.
Precisely. Byzantine consensus is really all about establishing trust, even in the presence of distrust. It's like designing a voting system where rigging the results is virtually impossible,
Right.
even if some voters are trying to cheat.
Right. Okay, that's incredibly clever.
It is.
But are all Byzantine consensus algorithms created equal?
Well, not exactly. There are different types, and they have their pros and cons. So one classic algorithm is called practical Byzantine fault tolerance, or PBFT for short.
PBFT, I have heard that name before.
Yeah, it's a common one.
Okay.
And it's known for being relatively efficient in terms of communication overhead.
Got it.
But it can be a bit more complex to implement.
Okay, so there are trade-offs, like with everything else.
Always trade-offs, yeah.
Right.
Another example is delegated Byzantine fault tolerance,
Okay.
or DBFT.
BB.
And this one aims to improve scalability
Okay.
by delegating the consensus process to a smaller group of nodes.
So it's like having this representative group making decisions on behalf of the larger group.
Exactly.
Okay.
And by reducing the number of nodes involved in that consensus process,
Yeah.
DBFT can potentially handle larger and more complex systems.
So it seems like there's this whole world of Byzantine consensus algorithms out there,
There is.
each with its own strengths and weaknesses.
Exactly. And choosing the right one
Yeah.
really depends on the specific requirements of the system that you're building.
That makes sense.
Yeah.
So this has been incredibly enlightening.
Yeah, glad.
I'm starting to see, we've been talking a lot about consensus algorithms.
Yeah.
And you mentioned data consistency earlier.
Right.
Can you elaborate on what that means?
Sure.
And how it relates to all of this?
So data consistency is all about making sure that those multiple nodes in a distributed system
Okay.
all have a shared understanding of the data. And there are different levels of consistency, and the choice of that consistency model depends on the needs of the application.
Right. So it's about ensuring everyone's on the same page data-wise.
Exactly.
Okay.
One of the strongest forms of consistency is called strict consistency.
Okay.
And it guarantees that any read operation will always return the most recent value written to a data item, regardless of which node you're reading from.
So it's like having like a perfectly synchronized system.
In an ideal world, yes.
Right, where everyone always sees the same data.
Yeah, but achieving strict consistency can be very challenging.
Okay.
And it often comes at a significant performance cost.
So it's not always the most practical approach then.
Right.
Okay, so where does sequential consistency come in?
So sequential consistency is a slightly more relaxed form of consistency,
Right.
but it still provides strong guarantees.
Right.
It ensures that all operations performed by a single process
Okay.
on a data item are seen in the same order by all other processes.
So it's like making sure that each process sees a consistent timeline. then...
Yeah, a consistent timeline of its own actions.
Oh, yeah.
Exactly. And it's a bit more flexible than strict consistency.
Okay.
Making it a bit more practical for many applications.
Right, so it seems like there's this trade-off between the level of consistency...
Yeah, there is.
and the performance of the system.
There is. That's a really key consideration when you're designing these distributed systems.
Yep.
You need to choose a model that kind of balances the need for accuracy
Right.
with the need for speed and efficiency.
That makes sense.
Yeah.
This is all starting to make a lot more sense to me now.
Good.
Consensus algorithms and data consistency are clearly very fundamental concepts in distributed systems.
Absolutely.
They're like the unsung heroes,
Yeah, they really are.
enabling all these technologies that we rely on every single day.
That's right.
Welcome back.
It's great to be back. Before the break, we were talking about how these algorithms are applied in real-world scenarios. You mentioned databases and cloud storage.
Can you give us some more specific examples of how consensus plays out in those areas?
Absolutely. Let's start with distributed databases. A common challenge in these databases is ensuring that data is replicated consistently across multiple nodes.
Right, because if different nodes have conflicting data, it could lead to all sorts of problems.
Exactly. A popular distributed database called Apache Cassandra uses a consensus mechanism to address this challenge. It employs a gossip protocol where nodes exchange information about the data they hold.
So it's like a network of gossiping friends, making sure everyone has the latest scoop.
That's a great analogy. Through this gossiping process, Cassandra ensures that all nodes eventually converge on the same data, even if some messages are delayed or lost.
So it's like a self-correcting system that keeps the data consistent across the entire network.
Exactly. Now let's move on to cloud storage services like Google Drive or Dropbox. These services face a similar challenge.
Right. They need to make sure that your files are synchronized across all your devices.
That's where consensus algorithms come in. These services use algorithms to manage the replication and synchronization of data across their vast data centers.
So even though we might be accessing our files from different devices in different locations, we can trust that the data is consistent thanks to these algorithms.
Precisely. And it's not just about keeping files in sync. Consensus algorithms also play a role in ensuring that data is reliably backed up and protected against failures.
Makes sense. If one server goes down, the data is still safe and accessible because it's replicated on other servers.
Exactly. And this redundancy is crucial for services that handle sensitive and important data.
Now, we've talked a lot about traditional distributed systems. But what about blockchain? It seems like consensus is at the very heart of how blockchain technology works.
You're absolutely right. Blockchain relies heavily on consensus to maintain the integrity and security of the distributed ledger.
Can you remind us how that works? What are the key consensus mechanisms used in blockchain?
Sure. The two most common mechanisms are proof of work and proof of stake. Remember how we talked about them earlier?
Yes. Proof of work is the one where miners solve complex puzzles to add blocks to the blockchain. And proof of stake involves validators who are chosen based on their stake in the cryptocurrency.
That's right. Proof of work, as you said, is a computationally intensive process. It's like a race where miners compete to solve a puzzle, and the winner gets to add the next block.
So it's a way of ensuring that only valid blocks are added to the chain, because it requires a significant investment of resources to do so.
Exactly. But this comes with the trade-off of high energy consumption. That's where proof of stake comes in. It's designed to be more energy efficient.
Right, because validators are selected based on their stake, not on their ability to solve complex puzzles.
Precisely. And that makes it a more sustainable approach in the long run.
So both proof of work and proof of stake are trying to achieve the same goal-reaching consensus on the blockchain, but they use different methods with different trade-offs.
That's right. And the choice of mechanism depends on various factors, like the specific goals of the blockchain, its scale, and its energy consumption considerations.
It's fascinating how these different consensus mechanisms have evolved to address the unique challenges of blockchain technology.
Absolutely. And as blockchain continues to grow and evolve, we can expect to see even more innovative consensus mechanisms emerge.
Now, before we move on, I want to circle back to something you said earlier about the importance of choosing the right consensus algorithm for a particular system. Can you elaborate on what factors need to be considered when making that decision?
Sure. Choosing the right consensus algorithm is a critical design decision. One of the key factors is the fault tolerance of the system.
Fault tolerance, meaning how well the system can handle failures.
Exactly. If the system needs to be highly resilient to failures, then a robust algorithm like Paxos might be the best choice.
But you mentioned earlier that Paxos can be quite complex to implement.
That's true. So if simplicity and ease of implementation are priorities, then Raft might be a better option.
And what about performance? How does that factor into the decision?
Performance is always a key consideration. Some algorithms are more efficient than others in terms of communication overhead and the time it takes to reach consensus.
So if the application is sensitive to latency or requires high throughput, then the performance of the consensus algorithm becomes even more critical.
Exactly. And finally, you need to consider the security requirements of the system. If the system needs to be resistant to malicious attacks, then a Byzantine fault-tolerant algorithm is essential.
So it's a balancing act, weighing the trade-offs between fault tolerance, complexity, performance, and security.
That's right. There's no one-size-fits-all solution. The best choice depends on the specific needs and constraints of the system you're building.
Now, we've talked a lot about how consensus algorithms are used in different applications, but I'm curious about the broader impact of these algorithms. How have they shaped the way we think about building reliable and scalable systems?
That's a great question. Consensus algorithms have had a profound impact on distributed systems design. They've enabled us to build systems that are much more resilient to failures and can operate at a much larger scale.
So they've played a crucial role in the evolution of the internet and cloud computing.
Absolutely. Without consensus algorithms, many of the services we rely on today simply wouldn't be possible. They've allowed us to move away from centralized systems that were prone to single points of failure.
And they've paved the way for the development of new technologies like blockchain, which is inherently decentralized and relies on consensus to function.
Exactly. Consensus algorithms have truly been a game changer in the world of computing. They've enabled us to build systems that are more reliable, scalable, and secure.
And it seems like their impact will only continue to grow as we become even more reliant on distributed systems and technologies like blockchain.
Absolutely. Consensus algorithms are a fundamental building block for the future of computing.
This has been an incredibly insightful journey into the world of consensus algorithms, but I know there's always more to learn. What are some key takeaways for our listeners who are new to this topic?
Well, first and foremost, remember that consensus algorithms are essential for ensuring agreement and consistency in distributed systems.
So it's about bringing order to the potential chaos of multiple nodes operating independently.
Exactly. They're the invisible force that keeps everything in sync.
And these algorithms are used in a wide range of applications, from databases to cloud storage to blockchain.
That's right. They're everywhere, even if we don't always realize it.
Another important takeaway is that there are different types of consensus algorithms, each with its strengths and weaknesses.
Choosing the right algorithm depends on the specific requirements of the system you're building.
So it's about understanding the trade-offs and making informed decisions.
Exactly. And finally, I think it's important to appreciate the ingenuity and creativity that has gone into developing these algorithms.
They're a testament to the power of human ingenuity in solving complex problems.
Absolutely. And as we continue to push the boundaries of computing, we can expect to see even more innovative solutions emerge in the world of consensus algorithms.
I can't wait to see what the future holds for this fascinating field. But for now, we're going to take another short break. When we come back, we'll wrap up our deep dive with some final thoughts and explore some resources for listeners who want to learn more about consensus algorithms. Don't forget to like, share, and subscribe to The Deep Dive for more explorations into the exciting world of technology. We'll see you in part 3.
See you soon.
Welcome back to The Deep Dive. We've been on quite a journey exploring these consensus algorithms.
It has been fascinating.
It really has. And before we wrap up, I'd love to give our listeners some practical advice.
Okay.
For those who are brand new to this topic and they want to learn more, where should they even begin?
Well, there's a ton of info online and in libraries.
Yeah.
I think a great starting point is to look for some introductory articles or videos that explain the basic concepts in a simple, accessible way.
Yeah, so don't be too intimidated by all the technical jargon.
Exactly.
There are resources out there.
Yeah, they break it down.
Yeah, for beginners.
Once you've got those fundamentals down, then you can start digging deeper into specific algorithms,
Okay.
like Paxos or Raft or Byzantine consensus.
Yeah.
There are a lot of great research papers and blog posts,
Yeah.
and even online courses that explore these algorithms in detail.
Okay, great.
And if you're more of a visual learner,
Yeah.
there are some great videos and interactive simulations out there
Okay.
that can really help you visualize how these algorithms work.
Right, like see it in action?
Yeah, exactly.
That's awesome.
Yeah, and don't forget about the power of community.
Oh, yeah.
There are so many online forums and discussion groups
Right.
where you can connect with other people who are interested in this.
Right. Bounce ideas off of each other.
Exactly. You can ask questions, share your own insights.
Yeah, it's really cool how accessible, like, all of this knowledge has become
It is.
with the internet.
Yeah,
But there's so much information out there.
there is.
It'd be kind of overwhelming to know, like, where to focus your attention. So any advice on what aspects of consensus algorithms are particularly relevant today?
That's a good question, I think. Given the rise of blockchain technology
Yeah.
and the growing interest in decentralized systems,
Right.
I think it's really important to understand Byzantine fault-tolerant algorithms.
Right.
Because they're specifically designed to handle situations where some participants might be malicious,
Yeah.
unreliable.
Which is a very real concern,
It is.
especially in, like, these decentralized environments.
Exactly.
Right.
And as blockchain continues to evolve, we can expect to see like even more sophisticated consensus mechanisms.
Right. That makes sense.
Yeah, so staying up to date in this area is important. It can give you a real advantage in understanding like the future of technology.
For sure.
Yeah.
So I think we've covered a lot of ground today.
We have.
From basic concepts to real-world applications.
Yep.
And the future of consensus algorithms.
It's the future. Yeah.
Any final thoughts you want to leave with our listeners before we sign off?
I think the biggest takeaway is that these consensus algorithms, they're not just some abstract theoretical concept.
Right.
They're really the driving force behind many of the technologies we use every day.
Yeah.
So the next time you're using a distributed database or you're accessing your cloud storage or you're even interacting with a blockchain, take a moment to appreciate the ingenuity of these algorithms that make it all possible.
Yeah, they're really quite fascinating when you, like, stop and think about the complexity of it all.
They are.
And how it just works seamlessly in the background.
Yeah, it's amazing.
So it's been a very enlightening conversation. I've learned a lot, so thank you.
You're welcome.
And I hope our listeners are leaving feeling empowered to kind of go out and explore this world a little bit further on their own.
I hope so, too.
Well, that's it for this week's episode of The Deep Dive, so be sure to like, share, and subscribe for more deep dives into the exciting world of technology.